Hello, Florida.
Hi.
Morning, man.
Ready to slay it?
So if you want to sleep,
Lots of you could
Yeah, I think so. I got this all calibrated last night, brought it all up, got it all set up. I wish I'd have got my PV and my switches are going to help, but I didn't. That's okay. They were only for the disconnect for the battery, so. What about you? You ready or what?
didn't get much sleep this weekend, so running on fumes right now. Hoping that just want to get through it. Check this question out.
I'm gonna turn the lights off real quick.
What time is it?
No, I don't know, but I'm gonna turn the lights off real quick. I think. Sure, the calibrator for the light.
Did you pay the power bill?
That was me.
You didn't pay the power bill?
No.
Okay, I'm gonna be watching from home, okay, 'cause my son's sick. I'm gonna be watching anyway. So if you don't see me here, it's not because I don't like it. Okay? Okay. I'm watching your presentation from home today.
Okay.
So I'll send my questions and disconnect it. Okay?
Yeah, I know, man. Looking sharp though. Looking clean as fuck.
There.
Yes. That's what it is. Just I love this a little more broad line. Maybe. I also think there's a difference trying. So I got like the new ones for me. He also got some of those for himself. I got mine. You have no idea how many cigarettes you try. Like, electrically, you go here, you go, for no fucking reason, just that not work anymore.
Guys, the mic's on. You can talk, just watch it on.
going all in. That's a visual song. Yeah. Well, you never have to choose on one before. Yeah, so that's a little bit. Because as of now, we choose like every week. And it's still like, I mean, the big thing was like the front page, but still, it's ridiculous.
It worked right up until it just shut off.
And I can also Holy charge. They're cheaper, but with these, yeah, one of these is not the other one. They're going to say like if these ones last as much as these ones, we get like these. No, he's the one. He's the one.
I don't really see anyone else.
My gosh. I got two calls for things that wants to see. This is invisible.
He's the happy price.
You said the stream was working on it.
Hey, yeah, what you did. Yeah, like some. It's a little artsy drum. Boom. Back flip and legs.
What's it?
The one down like
Yeah, see how it's got us.
yeah. Yeah, I like it. baseball diamonds, soccer fields.
Yeah.
Alright, morning everyone. It's now Monday, May 29th. We're nearly at the end of our SPL Symposium. It does continue until tomorrow. This morning we have the gratitude to have Nathan Boudreau present his climate controlled greenhouse. Take it away.
Good morning, staff, students, advisors, and anyone else who may be joining us today. So today I'm here to talk to you about my climate-controlled greenhouse. But before I get into that, I want to do a little bit of an introduction about myself and who I am. So my name is Nathan Boudreau. I'm currently a student here at NBCC, taking the alternative energy program through the electrical engineering technologies pathway. With that in mind, I have been a student here, obviously for 2 years. I live in Riverview, New Brunswick, and I've lived there pretty much my whole life, just across the river, as many of you may know. And other than that, I feel that this greenhouse that I developed and project that I've made will be a great, will be a great contribution to my knowledge as a student. I guess is the best way to explain that. So, what is the climate-controlled greenhouse? What did I design it for? How did I design it? And what did I design it to do? The climate-controlled greenhouse is a greenhouse designed to grow plants in a controlled environment. However, specifically, I designed mine as a propagation style house. Well, what propagation is? Propagation is the early growth and development of plants, from seeds, clones, grafting, and as well as baby plants. That's all considered propagation. And with that in mind, when I developed my greenhouse, I developed it in a way to try to create stronger, healthier plants that can be transplanted outside into your personal garden, into large-scale growth, into farmers, and anywhere else that has the potential to grow plants. To do this, I had to come up with an idea, and I had to use basic knowledge that I'd already had in order to figure out how to make a stronger, more resistant crop in order to plant outside with the greenhouse. And to do so, I developed the climate-controlled greenhouse. Now, the climate-controlled greenhouse that I developed, I chose to do this, again, for personal interest, because I find plants are super interesting. I've grown up my whole life around flowers and plants. My grandfather was a farmer, my grandmother, same thing. My parents live in the country, so to me, it just kind of naturally made sense to use my personal interest in plants to develop this sort of process, because I was able to use underlying knowledge that I already had to develop something that I feel works for my needs. And to use this, I used a little bit of my background in horticulture, where I have an applicator's license. I've worked in the horticulture industry, and I've also worked in watering and places like that, where they do that sort of thing with help transplanting plants. So basically, my thought was by building this greenhouse, I can create a sustainable, cheap product that can be used for people and anybody to adapt to any sort of system they have. Because the system I developed is simple, it's small, and it can be modular. And it's simple, it's small, modular, and can be connected to a pre-existing growth operation from large scale to home scale, where it's just a simple circuit I've developed that plugs in and can be attached to anything else. And with doing so, one of the biggest aspects I found was cost savings. In order to do this in a cost-saving manner, I had to figure out what's the cheapest way to do it. And the cheapest way to do it to me, I found, was just using basic ICs, basic circuit, and just a basic simple circuit designed to do the exact same thing that you could do with a microcontroller, however, obviously on a smaller scale because it isn't digital, and I was thinking along the scales of PLCs and everything else like that. But to save money, I thought a simple basic circuit was the best way to do this. So how I built this and why I came up with the idea, how I built this after I'd come up with the idea of my simple comparator. The first thing, obviously, was the idea, which I've just explained to you. And a little bit more of how I fell into this idea is I have a whole bunch of plants at my grandmother's. I was trying to figure out how to plant outside, but it was fed early in the year and I don't have space. So what do? I can't put them outside into a greenhouse. I can't leave them inside. But I thought maybe I could develop something that I could use a little bit earlier in the year to put my plants outside to help grow stronger plants before I plant them in my garden, obviously. And to come up with, once I had the idea in my mind and how I was going to do it, what I was going to do, I had to come up with how I was going to do it. And the best way to determine how I was going to do it was utilizing a block diagram, obviously. Because with the block diagram, I can take my structural concept that I had in my mind, write it out, develop myself a flow, and from there take that flow and put it into a diagram that allows me an easier way to view the information that I have and I've thought to myself and how I want to present it. So once I determined that block diagram, the next step was to isolate major components that I thought I was going to need outside of my comparator circuit. Not only did I need to isolate the components that I knew I was going to need for my comparator, but I also had to isolate external components that I knew that I would need in order to make this project presentable, modular, be able to showcase what I've developed, and also to be able to put it into use. So with all that in mind, my next step was to create a schematic. Knowing how I wanted the comparator to act, and knowing how I wanted my circuit to basically regulate itself, I was able to take that knowledge, as well as the knowledge I've gained here at NBCC from my instructors, to be able to create a simple schematic, as well as a simple circuit that fit all of my needs. So, after I had created the schematic and the circuit, the next step is obviously to build the product, involving ordering parts, going to local suppliers to determine information, as well as to possibly get all information I could from everybody else. And at that point, we began the building of the project. So, with that in mind, we're going to go back to the block diagram where I will explain a little bit more in detail the steps I took along the way before I developed the schematic. So here we have, Yes. So, with that in mind, first thing obviously, knowing I wanted to do an alternative energy system where my specialization or pathway, I guess, is alternative energy, I thought the best thing for me and my needs was a PV system. So I borrowed a PV panel from the lab, I figured out how big it was going to be, and from there I tried to scale the rest of my system to fit to the one PV solar panel, 100 watts, I was able to acquire. And with that, I also was able to borrow a PV switch from Mr. Legier from the lab, or not a PV disconnect switch, sorry, a charge controller from Mr. Legier in the lab, and those two I was able to pair together. However, in order for my system to work, now that I had the PV panel and the charge controller, I also needed switches. I needed a PV disconnect switch. Even though I only had one charge controller, I thought for safety reasons it would be good to have a single switch where I could disconnect the system from the outside of my shed, just in case something was to happen. Secondly, I also needed a battery disconnect switch where I would be able to turn on and off the system and isolate it from the not turn on and off, but isolate the system from the battery in case the battery ever needed to be changed or work needed to be done within the system itself. With that, I was able, after ordering a battery disconnect switch and a PV disconnect switch, I was able to find myself a battery. From local suppliers, I was able to go out and able to purchase a used battery, actually, from a local supplier, like I said, where they changed the batteries out from call centers. So the battery I purchased is a refurbished battery from a call center that I was able to purchase for a very discounted price, and it was great. The battery I purchased meets my demand for sure, if not over, where it's 140 amp hours at 12 volts. It's pretty large considering my need for my system is, I'm really only putting about 60 watts out of power. I'm only pulling about 60 watts of power in total. And that power is also being used during the day while the PV system is running, collecting power. From there, after I had figured out basically how I was going to power the system, the next step was taking the system and figuring out how I wanted it to work. Now, one of the factors I was having with my comparator, one of the problems I was having with my comparator is false triggering, because I wanted my system to work from day to night. When as the sun comes up, it turns on to a certain point, allowing for fans and lights. And then as the sun sets, it would turn off, shutting off fans, lights, and all auxiliary components. But in order to alleviate false tripping, I had to incorporate a timer relay. Now the timer relay is programmed to the Farmer's Almanac to the date that I had planned to put my plants outside myself, June 10th. And that date we have sunlight from 4:50 a.m. until I believe it was 10:40 p.m. So my system only triggers from 4:30 a.m. until 11 p.m. That way, if some kids are walking through my backyard due to where I live, or there's cars driving by, the lights shining from the vehicles, or a flashlight, or a cell phone, or even my house will not trigger the system during the nighttime, henceforth stopping my plants from having potential issues that could arise from having light hit them on and off. Because plants are very sensitive to that, and at nighttime you can actually cause your plants harm, damage, genetic defects, and all kinds of other issues that could arise by causing your plant to wake up at nighttime and then go back to sleep, basically, is what you're doing. After figuring out what timer I needed, and after figuring out a timer to program my system, the next step was how I wanted my system to run. So I realized that in order to have a proper grow light and grow system, 12 volts didn't fit my needs. I could not find a very good 12 volt light that had a very good footprint that was designed for vegetation. So I had to upscale to 120 volts using a DC to AC inverter. That inverter allows me to access to 12 volts. Well, the inverter doesn't allow access to 12 volts, but the inverter uses the 12 volts from the battery, allowing me access to 120 volts. It's giving my system the ability to produce 120 and 12 volts. So from there, after I determined how much power my two power factors for my system, I say power factor, but I mean how my power is put out, I had to build my comparator circuit. Now the comparator circuit we're going to touch on more in depth a little bit farther on in the presentation, but for now I'm just going to give a quick rundown. But basically the comparator utilizes internal, external temperatures to activate the actuator, which activates my window, and it utilizes a single LDR sensor, which activates both the fan as the sun comes up, as well as activates my grow light based off of the light conditions. From there, once my comparator is triggered and utilizes the parts of the system that it needs, it activates my 3 external relays, and my 3 external relays are connected to my auxiliary components. For this system here, I've chosen for my auxiliary components to be a fan, window actuator, and a light. So with that in mind, that basically covers how I came to develop my system through my block diagram. So the next step after that, like I had said, was the comparator. Because now that I had figured out how all my major components worked, I had to figure out how all my, I say major, but I mean bigger components. I had to figure out how all my smaller scale components worked. And to do so, I basically used a simple IC, an LM339, op amp with 8 inputs and 4 outputs. And with that, I was able to utilize, we'll kind of go through the circuit from left to right. I was able to utilize, on this part here, 2 temperature sensors, which compare internal and external. They're both 10K NTC thermal probes. And they basically, one is put inside the greenhouse and the other is outside. As the temperature of the greenhouse rises, and it gets higher than the outside temperature, it will close the window, allowing for that heat to stay within the system itself. When the external temperature is greater than the internal temperature, the window and the actuator will open, allowing for that fresh air to go into the greenhouse to allow for fresh, warm air to keep your plants warm at nighttime and throughout the day in cooler conditions. After that, the next part of the circuit is the light system, and that is all through here. So basically what I did here is I utilized a single LDR right here, and that single LDR goes to the positive and negative inputs of two separate parts of the comparator, allowing for the system to turn on once it dictates a little bit of light, activating the fan. And when the fan activates, it also sends power to the rest of the system, allowing the rest of the system to trigger as well. So that way, if the fan has to be on for everything else to activate, basically. So utilizing that, I then once I knew my system was going to be on and the light was on, I had to determine when I wanted the light itself to turn on. So the light itself is I've calibrated it in a way for myself that it turns on after there's about 20% light exposure, ambient light outside. So it won't be pitch black, it has to be a percentage of light outside for the grow light itself to actually turn on, as well as the fan. Once they turn on, the grow light and the fan will turn on under low conditions until such a point as we reach approximately 80% daylight conditions. At that point, the light itself will shut off, and the fan will stay running, and the system itself will also run. Because there's a point where obviously my light is not going to put out more light than daylight, and I don't need it, so it's a waste of energy to use it. So that energy can be put back into the system by saving it, obviously, to allow the battery to charge. With that in mind, I have my three outputs. One of them goes to the fan, right here. This one here is outputting to the light, and right here we output to the actuator. So with the light, I found that one of the big things I was having is that I would get false triggering if like a shadow or something goes by real quick. So to alleviate the light from flicking on and off and potentially burning up the light faster, I added a capacitor, kind of like the same concept as a decoupling capacitor, just to give a chance for the circuit to discharge a second before it actually completely shuts off. Hopefully alleviating something like a leaf flying over and just kind of clicking the system on and off real quick. So next, we have the build on the inside. And after I designed my comparator and built my comparator, which ended up being put into this case here, I had to mount all my components in two panels. Now initially I planned to use a single panel, but obviously due to the size of my inverter, I misscaled the first panel basically. So I had to purchase a second one primarily just for the inverter. With that in mind, after I put the inverter over into its own box, I was able to easily mount all the main components in here. The charge controller was mounted, as well as my two rails for positive and negative. I got an arc fault grounds, a GFCI arc fault circuit interrupter. I have my timer relay down here, as well as my 12-volt relays and a 120-volt relay. Sorry. So, small problems I've encountered during my presentation. Sorry about that, when I was taking the laser pointer off, I accidentally clicked and lost my presentation up there. So small problems I encountered. Some of the small problems I encountered throughout my project was that I found it awkward to be able to calibrate the LDR to function where in my range. And if I was going to do this again in the future, I'd probably use one with a wider range of resistance, as well as change the pot values that I use for my high and lows. That was one small problem I encountered. Another small problem I encountered, again, like I had said, was the size of my panels. I should have purchased one larger box. However, I made a mistake in my measurements, and I assumed that the diameter that was given in the dimensions wasn't the plate on the inside, but the diameter that was given in the dimensions of the box was the plate on the inside, where I was mistaken. It was actually the diameter of the whole box itself, and not the mounting plate. Those are some small problems I encountered. A major problem I encountered throughout it was I found that my transistors were getting super hot when I initially when I initially designed the system. And that was because I had designed the system using PNP transistors instead of NPN. So every time I would get it, it would do weird, funky things. It would get super hot, and I would put my hand over and I could feel the heat coming out. So that, once I started looking into it, I realized I needed to change my transistors from PNP to NPN. And in order to do so, obviously, I needed to order new ones. But when I was in the process of ordering new ones, I kind of come to realize that this project was going to be stored outside. I don't have a lot of cooling. So I upscaled the transistors from a 40 volt, 200 milliamp style PNP to a 1.5 amp, 25 volt NPN transistors. And I found by doing so, I alleviated a lot of the heat from the transistors, as well as only cost me like 20 cents more per transistor. And again, by doing so, exactly. Another major problem I had was figuring out how to get my project here. I initially had designed it to be a bigger scale project, but after a little bit of trial and error, and back and forth with my advisor, we obviously determined that this was the best place to present it so that all of you could see it. And also, in order to do so, I had to design it to fit here, basically. Through doors, in the elevator, and everything else. Which really wasn't a super major problem, but obviously it was time consuming to figure it out and get it all done. But I feel I did a pretty good job myself. So, let's move right on into after the build. So after I finished building my greenhouse, some of the things and observations that I've noticed were, like I had said, the tripping. Sometimes I find that even still adding that capacitor into where I had put in the comparator, I find that I do still get some false tripping. And that's, I feel, could have been addressed had I have maybe implemented a resistor with the capacitor to kind of make more time discharge of the capacitor, as well as using a larger capacitor. And also another note that I noticed, I'm going to go back real quick just so I can show, is that I should have added a diode, just so that when it goes to negative, I'm not getting the capacitor discharging in both directions. I know that I have a resistor that does help as a voltage limiter, but at the end of the day, I still am basically discharging kind of in both directions. And it would have been nice to be able to block that off completely and have my capacitor here kind of discharge through the system completely, alleviating any false tripping, as well as potentially maybe adding it to a 1 or 2 second delay versus 15 milliseconds or whatever it is. Other observations I had is I found that for the time of the year, thank you. Yeah, all right. Sorry, I'm not very good with PowerPoint. Sorry. It's completely frozen up here. There we go. Yeah, sorry about that. It froze on me. Yeah, so observations and testing. Like I had said with my observation, I had found that the capacitor was too fast to discharge, not allowing for some bigger objects to pass over, maybe like clouds and stuff. Would have been a nice thing to compensate for. Another observation I found is that when I was designing the system, I didn't put a pot in to be able to calibrate between the internal and external temperatures. So where I used two 10K NTC transistors, or thermoprobes, I keep calling them transistors. Where I used two 10K, the thing is they're not exactly 10K, right? So I should have added two pots, one for the internal and external, so I could have get a little more calibration. Also, I noticed that by adding a cable from here to there versus the one that initially was on the transistor, obviously I get more resistance as well through the cable, and that would have been nice to be able to compensate for as well. Just something to think about if I was to rebuild this project again in the future. So when it comes to testing and observations, I wasn't able to complete my testing due to my limitation of the weather outside, as well as how short of this time span I had by the time I had finished completing the project to this point. I was able to have it sit in my backyard and run for the week, and I did find that it worked great. I charged all week, and every day it was opening and closing as it should. And I also found that I was getting triggering for my lights at the adequate time in the morning. So when I would get up, I would know, when I got up early, I would notice the light would be on, the fan would be on, the system would be open, and then by the time I ate breakfast, the light would be off, the fan would still be open, the fan would still be running, and the system would be open. And there were a few days this week where I was testing to make sure the internal and external components would open and close as they needed. And they did, they worked great. As for testing itself, though, obviously, like I had said, I was unable to perform it. But some of the tests I was looking to do was I wanted to see what the internal versus external temperature difference would have been in order for my system to trigger the window to open and close. And another test I would have liked to have done would have been to actually determine if my calculations and what I had done were actually 20% light triggering versus 80% light triggering. These two parameters would be nice to know, just for my system alone. And one more test that I kind of wanted to do was just to determine the footprint of the light versus the footprint of the sun, and kind of the same thing that goes back into the last test where I have my on-off trigger points. Two style tests to determine the same information, basically more information for me. So after everything was said and done, and I was able to complete my final project, we get to this. The grand scheme of my project, all my hard work accumulated into about 47 parts, costing about $2,283. But that includes things like the lumber I used to build the system, screws, grow lights, the wheels, and everything I used to design to make it modular as well. With that, basically that's it for my parts. I mean, it's very, very self-explanatory. Some modifications I would make in the future. As I've said, I would like to add, I feel that the circuit needs pots for the temperature, internal and external. I also feel that it would have been nice to put knobs on the outside of the case for my actual calibration, so that I don't have to open it up to calibrate. Like when I brought it in here this morning, I had to open it up to calibrate it for the lights in the room. And if I move it outside, I have to open it up to calibrate the lights, the light for outside. And these are things that don't need to be done. I should have implemented two knobs right on the front of the case just to alleviate that issue. Another issue, modification I feel I would make in the future is I should have put external LEDs on the comparator just to be able to tell me this and this and this are happening. Basically, just to tell me like the fan's triggered, the humidity, or what's going on. Other than that, I feel that there are obviously lots of modifications that could be done to it through trial and error developing. I mean, this is stage one of something that could have multiple development issues. It could have digital display. I could have a digital display, but by adding digital displays or microcontrollers or PLCs, I feel like we're adding unneeded costs to the systems. So to me, maybe some simple modifications might have been a little bit better ventilation within the comparator itself, just to keep it cold on hotter days. So in conclusion, what did I accomplish? I feel to myself, I've accomplished the goal that I had set out to process. I built this climate controlled greenhouse. It's modular, it's portable, it does exactly what I want it to do. It opens and closes as needed. It triggers when there's low light, it triggers when there's high light, and it also triggers based off of humidity, so I feel I've accomplished pretty well what I set out to do. Now this system, I feel for potential future uses, obviously it can be used for cultivators, it can be used for farmers, because the comparator itself is the main system. That can be plugged into any other greenhouse to control the components within that greenhouse. All you would need is a timer and the comparator. If I was going to do this again, I'd also try to implement the timer right into the circuit itself. Other potential future uses, it could be potentially used in RVs to moderate the climate within the RV, or camping utilities. And I'm sure there are other possible creative outlets that this could be used for as well. So, having said that, I'd like to say thank you for your time, and now we'll move right into my demonstration. So for the purpose of the demonstration, I have a solar panel, but I did not connect it because I felt it didn't need to be connected for the purpose. There's no light in here. So, in here, because of the sunlight and stuff, it's hard for me, I couldn't quite get the calibration properly for it to completely shut off. So currently it's running at a low light condition. And then as I turn the lights up, the simulation starts coming up. The radar light shuts off, the fan stays on. Now we shut off, the fan was not the short of it. Now the fan would shut off normally if it got all the way to the temperature. With that, I also have my wire came loose when I was transporting it for my power. That's because it is still getting power, it didn't short, due to the fact that it actually closed, and it's a powered opening closing actuator. So the power to the actuator has to switch. Inside of my comparative is a little loose, so the power that the wire that goes into the ground is loose and came up there, and obviously I'm not going to fix it for the demonstration, I don't have time. But there is a temperature probe here, and this temperature probe would trigger the internal actuator to close the system as is. And the external probe I've mounted in the back, so that way they're on opposite sides. And when the external probe, again, like I had said, the actuator would reopen. And I guess with that, that's my demonstration where I can't show you how the actuator actually, well, I showed you, but I can't show you, again, with the heat gun, how the actuator opens and closes. So sorry about that. And yeah, I'd like to open the floor up to questions.
Bring up your slide.
No problem. I figured out how to use PowerPoint.
So you have you have 3 or 4 transistors there.
Yes.
Okay. I'm just curious. Could you please explain their interaction between themselves and as to how things trigger? Like I'll be honest here. Your terminal blocks there.
Yeah.
Yeah, they're laid out. The bottom ones are kind of laid out great. The only thing that you could have had is labeling for them. I don't understand which one is which.
Yeah, I threw it in the notes, but I agree. It should have been into here, a label with an arrow as well as pointing to the color of the wire and what it does.
Exactly.
I noticed that as well as an oversight. Another oversight I had before I get into explaining transistors is that when I switched my transistors from NPN to PNP, I negated to adjust the direction of the arrow. So these, yeah. But
these are
and they're supposed to be NPN. They're SS8855, SS8850s. So they're supposed to be NPN instead of PNP. And initially, like I said, when I inverted the system, I negated. I didn't notice the arrows; they were an oversight, basically. So what happens is, as the fan, when the fan triggers and turns on, it sends power to. When the fan triggers and turns on.
So what triggers the fan?
Sorry. So as the daylight comes up, when we get to the point where we have 20% ambient light right here through my LDR, we trigger the fan.
Oh, okay, there's a node.
Yeah, they're not very large in this diagram. It triggers the LDR, and the LDR triggers the comparator, sorry, which triggers the activation of my fan. And as well as it also triggers the activation of this transistor here. This transistor is my power transistor. It sends power to the other two transistors. So basically, if my fan doesn't trigger, even if these turn on, they won't have power going out to the relays. The fan itself needs to be on in order to trigger the other two. So basically, once the power goes this way through here, and then as well as it activates this one and this one here.
And then those two are activated by what?
And then this one here and this one here. This is my highlight level. So as the light gets to approximately 80, as the daylight gets to approximately 80%, this is what triggers. This triggers the LDR, or not the LDR, sorry. I keep saying LDR. This triggers the grow light to shut off.
Okay.
Because due to it being due to it being an inverting, right? So it triggers. And then this one here is triggered by my internal and external temperature probes. And basically, I just compare between the two. So when one's higher than the other, it either triggers or shuts off the actual system.
And the purpose of D3?
Diode 3, I found, because it was connected to the actuator itself, I put it in there just to make sure that it's on, off. I didn't want, because I get inverting and non-inverting pulses, right? So I just did it basically as a point, so it's a threshold level to ensure that when the actual actuator triggers, it triggers, and it's basically I didn't want it's due to an analog, right? I didn't want my voltages to be kind of like, say the outside one went to 43.6 and then 42.4 and then back up to 43. I found the diode allowed for kind of that 0.7 voltage increment that allowed, just to make sure that I'm at the point where I want my actuator to turn on and off, basically. Yeah, it's just kind of to increase the voltage going, it's kind of to make sure I hit a threshold point. It doesn't increase the voltage going to here, but it makes sure that the voltage coming out of here is high enough that I don't...
Voltage coming out?
Or going in, sorry, opposite direction.
Going in, voltage is going somewhere?
Well, it's moving, I guess.
Voltage is moving?
Current.
Okay.
Sorry.
So that's what I don't get. The direction of current for me is...
It's a negative.
Right, exactly.
It's a negative.
Yes, exactly. I accidentally, when I did this, I created the system opposite to what I wanted. So my outside is inverting and my
So is it a positive 12 volt rail or a negative?
Positive 12 volt rail. So everything else in here works through positive. However, because I use the inverting, non-inverting, right? So when my diode shuts off, when one shuts off, it's hard for me to. I feel like I'm pulling it backwards. It's pulling backwards through versus pushing, right? So it's inverting and non-inverting.
So your inverter turns off to actuate the fan?
Yeah, the
Sorry.
actuator, exactly.
Okay.
Like I said, I utilized the signals incorrectly, negative versus positive. I wanted to use the positive end of the signal, but and all it is I just have to.
Well, it's not negative and positive, it's inverting, non-inverting.
Yeah, exactly. I use the inverting versus the non-inverting styles, and exactly. So to compensate for that, the diode.
So at TB2A,
Yeah.
you have a actuator relay.
Yeah.
That's being turned on and off.
Correct.
And we've had this discussion with other people before. What's the phenomenon that could cause issues here when you have a coil that's being turned particularly off, but on also?
Isn't it induction, like a reverse current that pushes against my signal, basically?
What does an inductor do? I guess.
It poses a change of current and also increases voltage.
So when you
Shut it off, I'd be opposing the change of the current.
So then how do you oppose that change of current?
In my relay?
Yeah.
Yeah.
How does your relay oppose that change of current?
Yeah, it doesn't.
No, it does.
It does? Itself?
The relay is the coil.
Yeah.
So how does it oppose the change? Q3, what does Q3 have to do to turn the relay off?
To turn the relay off, Q3 has to shut off.
Okay, so if it shuts off,
Yeah.
Therefore, how much current do we have in the system?
None.
Okay, well,
None, but
Zero,
yeah, zero,
right?
yeah, exactly.
Okay, so if it falls to 0, the inductor tries to maintain
The
the
same
existing current,
Yeah.
not voltage.
That's right.
So how does it maintain the existing voltage, current, sorry?
By opposing the change by increasing the voltage.
Increasing the voltage. So how much voltage do we need to maintain current if Q3 is, I don't know, 10 megs across or?
How much voltage do we need to maintain it?
Sure.
Probably 12 volts, I
Think
assume.
about it, how much current flows through that usually?
Right here, about 75 milliamps.
75 milliamps,
Yeah.
okay. So Ohm's law, 75 milliamps, 10 megs, how much voltage?
7 volts.
Around 70.
And meg, sorry, I'm thinking, yeah, 70, 700. Sorry, my math. I'm not great at math on stuff like that.
We can
Yeah.
ballpark it.
Yeah, about
You're
700.
talking about hundreds,
Hundreds of
if
volts,
not
yeah.
thousands of volts.
Yeah, 700, 7,000.
What's Q3's emitter collector voltage limit?
1.5 volts. Or 1.5 amps, 25 volts.
25 volts, so
Yeah.
we're in the hundreds of volts.
Yeah, so it's opposing that, and it's going back through the transistor itself.
No, well, no, you're applying hundreds of volts across two terminals that only can handle 25 volts.
I get it.
You're exceeding the specifications of that transistor by a lot.
Yeah, so I should have a diode or something down here as well.
Where should the diode be?
Down here.
Diode connects, no, not in series, no.
Parallel. Yeah, I should have a parallel one back through.
Not there, the diode won't work, it'll short your,
So back up to the volt up here, sort of thing.
no. What are we trying to protect?
Oh, okay, I'm trying to protect this
Q3 from what?
Q3 from overcurrent, right?
Well, no, but from what phenomenon?
From the opposing change
The voltage, the excessive voltage of what?
of the relay.
There you
Yeah.
go, so what should we be trying to?
We should be mitigating it by from the relay, probably going right to ground, right?
Exactly.
Yeah,
Exactly.
that makes sense. I felt like there should also be a few other diodes along the line.
Well, what's TB2B? It connects to an
Same
external
thing.
light relay.
Yeah,
right?
all three of these exactly.
TB2C connects to a fan relay, right? So you've got, is that what it is?
Yeah.
So all those are connecting to coils, and I can tell you Q3, Q1, and Q2, they're not gonna have a very long life.
Well, that makes sense. Yeah,
They're not gonna have a very long
it's
life.
definitely an oversight on my part.
Q4 too. Right? Can you tell me what C3 is all about? You mentioned C3, but I didn't get it.
I put in there to try to help mitigate the like when something passes over top of the sensor, I put it in to try to help mitigate that, but I found that the time, like I only used 450 nanofarads, and I find that I should have also added a resistor in it to kind of like a discharge time sort of thing. It's just, this isn't
I don't
really,
understand. So you wanted to,
it's just almost like a battery that just discharges if something goes over top, so the light doesn't turn on and off by like, I just didn't want to trigger on and off basically quickly out of nowhere. And it's to help discourage that.
so what kind of, so you put a capacitor there, but I
Yeah.
don't think your capacitor in itself alone,
No, it's not big enough, and it should have a.
because you need an RC time.
Exactly, yes, I agree 100%.
D2, what's D2 all about? I find D2 very confusing.
D2, that's just that's from my negative. That's going back out. It's the negative. It's on my negative rail from the whole circuit. It's just a diode to protect a protection diode for the output of the whole circuit. It goes because the diode goes from there directly to the terminal block, basically, and outwards. So,
Okay, but, so,
I don't really know.
again, for me, when I'm looking at schematic, I'm looking for left to right, top down.
Yeah.
So TB1 for me is something you're connecting from the outside world.
Yeah, it should have been up and out like that, and then these two connections.
Well, even, to be honest, your TB1 should have been pointing towards the left there. Like the-
Yeah, because this is actually supposed to be connected to that side.
And TB2, TB2B, and C should have been pointing the other way. Right, because they're outputs, right? It's left to right, top down,
I didn't know that.
right?
Yeah, I had no idea. I didn't know that they had to be. I didn't know that there was
Right,
that
we
direction.
talked all about that in missed the 3 or 4 times you talked about schematics and, you know. But definitely, TB1's the worst for me. For me to look at it that way is very confusing.
Yeah, I agree.
Anybody else? Is D2, yeah, that's, Mr. Broad, by the way, is reviewing remotely. He couldn't be here because of
Yeah,
a family issue. He's asking here, is D2 part of the PCB?
yes.
Okay, so again, you know,
Yeah,
the way it is there is very confusing. For me, it looks like it's just in series on the outside somewhere.
Yeah, exactly. But like I said, I feel I addressed that by stating that I should have been faced the opposite
Yeah,
direction.
well, if it was drawn properly, we might be able to know what it does. So what does it do again?
Protects the circuit itself from on the outgoing side of the circuit from current going back into the circuit. It protects it from basically when you connect here to here, it protects the negative side of the circuit. Basically.
What is the negative side here?
Well, not the negative, but as everything's grounding out, it stops anything from going.
Is
from
everything's what, burning out?
grounding out. I say grounding out, but what I mean is, as the current flows through the whole circuit and it's leaving the circuit, this diode alleviates anything from coming back in through the negative side.
What?
It's designed to stop things from going back in the negative side of the circuit.
Why would things go back in the negative side?
Exactly, that's why the diode's there, in case something was to happen.
No, why would things go back in the negative side?
Oh, from, I don't know, a short, or on the outside, possibly a short, if the, or
Well,
or
the
the
current's never
wires,
gonna get there if the short's on the
or if
outside.
the wires were connected into the terminal block in the opposite direction.
Oh, so it's for polarity reversal protection.
I guess so.
Yes, so.
Well, that's terminology to me. That's why I'm a student, right, to learn.
Yeah, but here's the final learning.
Yeah,
So
that's why,
you
right.
have an opportunity to learn.
That's why I'm still up here learning.
It's just an observation, not a question, but we didn't see any PCB design. Did you do a PCB design?
I did do a PCB design, but I just felt it redundant to put the PCB as well as the schematic where the PCB was just a comparator.
Was that just like an hour for you to do the PCB? Or?
Yeah. It wasn't
It only
real.
took you an hour?
It didn't take, well, no, it didn't take real long to make it. Like, it was just, I guess it took me quite a
Design
while.
it? And
Yeah, I
then-
guess it took me quite a while, but
No troubleshooting there?
I mean, to me, I had to mitigate what I could put into the presentation for my presentation time. And with what I have, I've already hit my allotted 30 minutes, so by adding more to it, it would be more for me to explain.
One more observation, you spent a lot of time on the introduction.
Yes,
You should have.
I guess so.
Just an,
Well, my introduction, I spent a lot of time was nervous. I had to get used to being presenting in front of a crowd, right?
I understand.
Yeah. This is my first time ever presenting.
Alright.
Yeah,
Good,
so.
that's good.
All right,
Thanks for your time.
thank you.
No, I just here's my card.
Bring extras.
Yeah, sure.
No, sí, pero hasta que termine la...
Dime dónde, porque se ve que si lo levantas, por dónde lo vas.
Sí, de aquí.
Porque ya ves que ¿dónde lo ves? De aquí.
Sí, yo creo que sí.
¿Dónde vas a querer poner?
Aquí es frente. Para demostraciones siempre hay más que sí. Vamos a hacer nada más un cachis. Es nada más para que no se...
Are you presenting over there, Jonathan? Are you presenting right there? I can do it.
Yeah, because I was confused, but I didn't. I know that everybody is scared out. That's what I did.
A ver, no se vaya a echar a andar. Ya se apagó. Entonces, primero hay que llenar
I see you. No, I see you open the door. Let me wheel this through.
I tried to open houses and everything right from this one spot. Because an example is the power panel loaded up by the capacity needed, but I'm not seeing it's not the capacity needed. There's something I'm missing.
I haven't looked at it.
Yeah, no, I'm saying that was
No, I'll see you at lunch.
Alright. How do you feel?
No, hasta ahí.
La otra igual.
Nada más, sí, está nada más. ¿Dónde están los
It's so cool to see.
¿Y la tercera? ¿Jonathan?
igual, nada más. Sí, sí, porque ahorita lo vamos a mirar ya bien. Dale.
¿Ya? ¿Ya? ¿Ya?
Mira, aquí está otra. Por si. Ya está. Y esta otra. ¿Lo vas a cerrar?
But it's so much fun though.
What's that?
It's a bad show. He also These judges.
I'm not an introduction phase, but if you want me, I can do it. Yeah.
You want me? I will say
Have to see it.
I think you're still.
Ready? You see? I'm clumsy.
Oh yeah, you might not be able to. I don't know if it's just real sound.
Not yet.
So
Hi, good morning, everyone. Here we have Mr. Alvarez here with his rainwater reuse automation system. You can go.
Okay. Good morning, everyone. Thanks to attend to this presentation. My final project is a rainwater reuse automation system. I am a student from NBCC. I am studying the electrical engineering technology, alternate energy pathway. This is the name of my program, as you know. Okay, this is my senior project, and I'm going to present my final project here. First of all, why I choose this project? So I wanted to choose an innovative and helpful project. So at the beginning, I was thinking, what can I do? Because to be honest, I didn't have any idea what kind of projects can I do. But after thinking, and and I realized that I like a lot all about circuits, electric control, motors, machines, and also I like the field of programming. So with PLC, I found the exact match between both fields. So I realized that I would like to develop PLC projects because they mix both fields exactly that I wanted to do. I didn't know at the beginning how to program or how to use PLCs, but I feel comfortable with my knowledge that I get before for all my teachers that I will develop a very good project. Also, to put a lot of effort. That's the answer that why I choose this kind of project. The purpose of my project. My project is to develop a system to optimize the collection, storage, and distribution of rainwater. So it's to catch water to reuse again in an apartment system. So it's focused in an apartment system, but we can reuse rainwater for a lot of kind of facilities. Okay, and to promote sustainable water management by minimizing the water waste. So again, is don't waste a lot of water and reuse rainwater. This is a big problem for example, my country in Mexico, that we don't have enough water, rainwater. So we don't have enough water. So it's a lack of water. So we need to storage water to reuse. So this is a sustainable, a very interesting topic. And to automate that system will help us a lot to achieve that goal. Okay. Before to explain my functional overview of my project, I would like to explain a little bit some issues, some problems that I had to face at the beginning of my project or during the process of my project. So I need to face a lot of problems. So I can't tell all the problems, but quickly I'm going to talk about that. The interconnection between the computer and the PLC, I thought that could be easy, the interconnection. So only to plug the PLC to the PC, to the computer, and install a program, and that's everything. But no. I was so confused. It doesn't work like that. So I need to reinstall an old system from my computer to see the PLC, and also I need to use a lot of kind of wires, because not all wires that look similar work similar, but it's not useful to use any wire. So this was one of the main problems that I need to face. Another problem, and it was almost at the end of my project, everything works very good. I test a lot of times the control panel with toggle switch simulating the sensor levels. But when I install the sensor level to my control panel, nothing works. And I didn't know, oh, what's happening, because I test a lot of time with toggle switch. So after testing all parts of my program and my devices, I realized that the wires was cut because I use a new tool that press the connector with the wire and unfortunately cut all my wires, and I need to resolve the wires and use another tool. But at the end, some problems happens, and we need to overcome those difficulties. Okay, now the functional overview. To explain in a better way the functional of my project, I split in two main parts: the hardware and the software. Okay, the hardware is all the equipment that I need to install to achieve our goal. So it's all the equipment installed inside my control panel. And to explain that, I'm going to explain the block diagram and then the wiring diagram, and helping with pictures. My block diagram is like that. Okay, this is I want to split in three main parts. This is the electric entrance, all these components, the inputs that are those components, and the outputs that are all these components. The electric entrance, my system works with 120 volts AC or alternate current, and then a protection device that is a breaker of 1 volt, 6 amps, and this breaker will fit the power supply that reduces the voltage from 120 volts to 24 volts DC current. And then another protection device for the 24 volts DC current, that is, I am using a fuse of 2 amps, and feed and energize the PLC. Also, the relays work with 120 volts AC current, the relays, and the relays, so the coil works with this voltage, but the sum pump works with the same voltage, but the coil of the relay works with 24 volts. That's why the both arrows in these blocks. And the relays feed, of course, when they are activated, the sump pumps. We have 4 sump pumps here: the rainwater catchment, the rainwater catchment filter, the treated water system or filtered water system, and the drain water system. And another outputs are the signals. So that is all the lights that I have to sign the status of the control. And for inputs, I have the sensor levels all installed inside the reservoir, the cisterns. We have 3 here, 3 here in this cistern. We have 1 in the drinking water and 2 in the roof tank. And the commands: the start, stop, and emergency push buttons. So those are all the equipment installed in the control panel. As you can see here, in a better way, the commands, the sensor levels, works as input, and the relays, pumps, and signal, that are the lights. And you can see in a better way where are located all those equipment. Yes, you can see here the sensor level, another sensor level in a different level of the container. The sump pumps, we have another sump pumps. It's so hard to see, but this black equipment is another sump pump, sensor levels, push buttons and pilot lights. The wiring diagram. So this is one of the most interesting diagrams to understand all the wiring involved in the control panel. That is the scope of my project. So here we can see the electric entrance, 120 volts AC current, the circuit breaker split in 3 lines, the line, the neutral, and the ground to the power supply. The power supply decrease the voltage and change the voltage from AC to DC current, and a protection device that is a fuse. Then, to figure out what is happening here, these are the outputs, the lights, and the coil of each relay that works with 120. In this point, we connect together in parallel all the wires with the negative side of my power supply, and the other side, the PLC will give me the signal, the positive signal, 24 volts to this point, and if we have the negative and the positive here, of course the light will turn on if the PLC sends that voltage. It depends of my program, of course, and the status of my inputs. So, as you can see here, the coils works with the same voltage, and the contactors works with 120 volts of AC current. So, you can realize that it doesn't matter which voltage or how many phases the motors or the pumps are designed to work. It doesn't matter. The only that I need to change is the contactor for another contactor that works with 3 phases or with more voltage. So with the same system, we can control large motors or small motors with the same system without any changes, only the power of the device. In the side of the inputs are almost the same, but no, it's not the same, it's almost. We have a positive signal here, comes from my power supply, and we don't have nothing here. But this is a switch. All the sensor levels and the push buttons works as a switch. If we close the switch, the current will pass, and we will have 24 volts positive, and my PLC will detect that we have a positive signal in each point, and depending of our program, will allow to have another positive signal in the outputs. That's the purpose of the PLC, and that's the purpose of the program, the code. So this is an expansion unit that only gives me more inputs and more outputs. So this is the wiring diagram. You can see that I explained you before some parts of the wiring diagram. And here we have the components inside to the control panel. So these are the terminal blocks. I divide in 3 sections. The control panel, this section are the power supply. This are the PLC, the main power supply, and this the inputs and outputs and the relays with sockets and some terminal blocks. So terminal blocks that we have 24 volts, the line, the neutral, 24 volts, the positive and the negative, some terminal blocks for grounding, the circuit breaker, the fuses, and another terminal blocks. The wire that you can see here is all the wires that come from the sensor levels. We have here the PLC. I am using the S7100 model from Siemens. It's an old model, so that's why I have some troubles to use this device, but at the end works okay. And my main power supply here. Terminal blocks. This is my outputs, inputs, outputs with the exact color code. And the relays and the socket. This is the socket, this is the relay that control the sump pumps. Why I not connect directly the pumps with the PLC? Because PLC can manage large amount of current. So usually the motors at the start demand a lot of current. This is not the case for my sump pumps because are very small, but in most of the cases we need to install an external device that controls my all motor machines. Okay, and to understand, let's move on to understand the software. I explained the hardware, so now I'm going to explain the software of my control panel. And the easy way to understand the software, I can explain the code that I want to try to do. I can explain the flow chart, but the easy way to explain how my control panel will work is to explain the process, the automation process. We have here the first reservoir, that is the catchment reservoir. Usually this reservoir is not going to get water only when it's raining. So then this is the filter or the filter reservoir, that in this reservoir we are going to store all the water from the rain. So here we catch the water, pass for a filter, and store the water from the rain. And this is the drink water, just in case. So we will need some water from this reservoir in case that we don't have enough water because it's not raining. And the roof reservoir here is at the roof of the building that for gravity will feed from water to all the apartments. So we need to push or pump the water from this pump to this pump. So we have some scenarios here that I want to explain so quickly. Okay, the first scenario, when it's raining a lot, okay, it's raining a lot, and maybe this reservoir is full. So what could happen? What could happen, and what can I do that don't overfill my system? Okay, this pump will pump the excess of the water to the street. So when this sensor is activated, this pump will turn on and will pump the water to the street. And the other scenario, when this sensor is activated, this pump will work and provide water to this container. Only when this container is full, if this sensor is activated, so this pump will stop. Another scenario, if we don't have enough water from the rain, and the level of the water is here, so that means that this sensor is activated, this pump will provide water to our reservoir, to this system, that is the filter system, because we need water. Not all the water, but we need some amount of water to be able to provide water to grow. And finally, when this sensor is deactivated, that means that this reservoir needs water. So we'll sense and activate this pump to start work and pump water to the roof tank. When it's raining, when it's raining and this pump is working and this pump start to work, okay, we have a special code that only will allow to work this pump. So my system will prioritize that this pump only works when it's raining. And for test purposes, I introduce a code that we can test if the electrician comes to the panel and try to test if the 4 pumps are working. The only that the electrician needs to do is to push the start button for 3 seconds, and the manual system will be enabled. And then push the push button 3 times, and the 4 pumps will start to work for 20 seconds only. Why 20 seconds only? Because to avoid that, if we don't have any water here in any reservoir, to avoid that the pumps don't work without water, or overfill if the 4 reservoirs are full, don't overfill the level of the water of the containers. Okay, this is the code that I use. Is mine everything, and I'm going to explain a little bit some key parts, some main parts of my code. For example, the emergency push button. If I push the push button, some pumps will work. So in this state, this is because the emergency push button is normally closed. So this will able, and my pumps that are here. So as you can see here, so this is closed, and my pump can work properly. Here, you can see for this. My pumps can work properly. But if this is disabled, some pumps can work. Another key point is the control manual mode that I explained you. If I push the timer for 3 seconds, my system will be, my manual system will be on, enabled. And I can do the second steps that I explained you before. These are more or less the key systems. These are the road to route. This is the bypass from this is the bypass that allows the 4 pumps works only for 20 seconds. It doesn't matter the status of the control sensors, the sensor levels. And this is my rainwater, the flow chart of my system. It looks complicated, but at the end it's not too bad to understand, but it's almost the same that I explained you before. We can see any sensor, if the emergency push button is activated. If yes, do another thing, turn on red warning blinking light, and check the emergency push button status. If not, check manual start push button status, and so on. But essentially, the process is that I explained you before, the flow chart. Okay, the part list. So to build this kind of project is not cheap. I spend some money. The school provided me some equipment like the PLC, but if a contractor or the final user wants to install a system like that, this is more or less the cost of the control panel plus the labor. So $2,400 plus the labor. So this is the cost of the project. For conclusion, this is a working success project. looks very similar that I imagined at the beginning. So this is my concept drawing. I imagine a process and the control panel like that. And at the end, I decided to build almost exactly that my idea. And looks like very similar. Of course, I need to adjust some equipment, but at the end, this is the original idea and the final results. So that's why, and everything is working properly. So that's why I think this is a successful project, because it works better, works very well. And let's move on for some improvements. So, of course, during the process of the building of this project, I can improve more and more and more. Unfortunately, I didn't have enough time to apply those improvements, but for example, I could use another type of level sensors for another that only I need to use one sensor per container per system, and will decrease the amount of inputs that I am using right now. It's involved that to decrease the amount of inputs. So also I can implement a screen, maybe over here, that showed me in real time the status of the main containers, maybe the treated water system or the roof tank, so to improve my project. So we can apply a lot of improvements at the end, but I think that this is a very useful project, because if we apply more equipment, of course the cost and the time of the design will increase a lot. What I learned during these 5 months of construction and design, I learned a lot, not only about PLCs, not only about circuits and motors. So I learned how to think an idea, apply all your efforts, and at the end get a very good result from your idea. I learned about the deadlines are very important. If not, you can improve and improve and improve, and you will never get the final result. I learned to put my best effort for every single project that I am developing. I learned ask for help. I learned how to research, because at the beginning I didn't know a lot of topics about this project, but I needed to research and understand. So at the end, I learned more than circuits and motors and PLC. I learned how to develop a success project. This is what I learned from this final project. Thank you. Thank you very much. Now, let's move on to the demonstration. Okay. Perfect. To turn on this equipment, only with the breaker and the power supply. And this red light will indicate that the system is enabled. Now, and at this stage, we can see that all my sensor levels are deactivated. So that's why my system requires water, but nothing is working because they don't have enough water to supply water for the other storage container. So that's why nothing is working. But as soon as I started to fill this water container, when the level of the water approaches to this level, the pump number 2 will start working to provide water to this container. No, more. Okay? More. And then help this. Provide water to this container. Provide water to this container. Then, because this needs water, the pump number 3 starts to work until this level. And stop, because we don't have enough water. Provide more water, please. More water. This container. Okay, let's test the pump number 4.
John, can you turn the camera over? Nobody online can see your.
Yes.
Just turn it to point towards you.
Has to be, yes, the presentation.
So now we have, is enough? Is enough to this container? So we have enough water to this reservoir. Yes? Okay. And this pump is still working because it's providing water from the reservoir to the other reservoir. And now, try to fill this container if you want, or put the you will see that the level of the water is decreasing, and when approach to this level, we'll start the another pump working again. And now we are going to test this sump pump when the level of the water decreases and it is not raining, this container will provide water from this reservoir to this reservoir. When the pump number 4 will start to work. As you can see. And now, because we don't have enough water, the pump number 4 can provide more water to the reservoir. Like that. Now I'm going to test the manual mode. To enter to the manual mode, the only that I need to do is to press this button for the sensor. Now the manual mode is enabled, and I'm going to press 4 times to start the 4 pumps at the same time. And the 4 push the 4 pumps. But this will be these pumps will work only for 20 seconds to avoid that don't waste a lot of time without water or to overfill the containers. Only 20 seconds. If I want to test again, only restart motor and 1, 2, 3, 4. And I can stop at any time. And of course I can stop all the system to the emergency system, and the blinking light will be in. And that's everything for my emergency. Now the questions section.
Just to clarify for me a little bit, so the water on the bottom come from the rain, is that what it is?
Yes, the water that we push that enter this reservoir is from the rain.
So the first one, and then you pump the
Yes,
other ones for
yeah.
for capacity,
Yes, yes.
and then you pump up to the
Yes,
building.
from here to here and from here to this reservoir.
Okay. Just, I wasn't sure of the sequence that's all right now.
Yes, yes, yes.
Yeah, I didn't really catch that either. So the one is catching the rainwater, the one on the left is filtered to
Yes,
like a storage.
filter and store all the rainwater that
The
I have.
last,
And the last is only clean water in case that we don't have enough water in this reservoir. So also we need water, so the system will take water from the reservoir. That is the worst case.
if it's not raining.
Yes, this is the worst case,
Okay.
but at the end is we need this reservoir.
Okay.
Okay, but only a certain amount of water. That's why the system stopped at this level, because we don't want to use all the water here only for these purposes, because it's clean water,
Right.
drinking water.
Okay. And when you were doing your demonstration, you said when you go in manual mode, it runs only for 20 seconds to avoid overfilling, etc. Do you have any other means to know if it is maximum filled? Do you have a sensor or something to say that it is full, the tank is full?
Yes, if the tank is full, all the sensors will be activated and nothing will work. Unless we activate the manual mode, the sensor will start to work for 20 seconds, as many times
So
as
if you're in manual mode, does it override your top fill sensor?
Yes, sure, but that's the purpose, that the pumps will work only for 20 seconds.
Okay, so if your tank is already full, you go in manual mode and you run it.
Yes, I can
It's gonna
overfill.
overfill.
Yes, but for example, this is a very small scale. Talking about a large scale, 20 seconds is nothing. It's nothing
Right.
talking about the filling of the containers.
Okay,
Yes.
thanks.
How did you determine this 20 seconds? Why not a minute? Why not 30
Okay.
seconds? Why not?
I use it's only a proposal time that if I am an electrician, I need to be sure that the 4 pumps are working. So it takes me only 20 seconds to realize that the pumps are working properly. So that doesn't take a lot of time to do that.
So it's just for testing purposes?
Just testing, maintenance purposes.
Did you do any testing?
Sure.
Testing?
Yes. My testing was only the amount of power of my system, the current and the voltage of the control panel. Those are my testing.
Yeah, you submit 2, so that's 1.
Yes. Okay, yes. This is the first one, and the other one was the efficiency of the level sensors. So the test was,
Efficiency?
yes, it's only, for example, at this level, the sensor will detect and stop, and test again, and if the second time will test again the same amount of water.
Well, that's accuracy.
Yes, accuracy, sorry, this is the,
Alright.
yes, the accuracy of each sensor.
Can you bring up your wiring diagram, please?
Sure. Okay.
Okay, you probably want to make that bigger because
Yes.
they're hard to read even with the full screen. All right, these are questions that come from Mr. Broad. He's reviewing remotely here. So he would like you to answer for output 404. Is that syncing or sourcing configuration?
Okay, yes, sure. The output number 4, yes. All my outputs, because we have, the answer is very easy, okay? Let me show why. So we have, because we have 24 volts for the negative side of this, and the positive will provide the PLC. So this is a sourcing configuration. So the PLC is the source of the voltage. That's why.
So which way does the current flow then?
Sorry?
Which way does the current flow?
Okay, the current flow from this point to this point. So we will have, if the PLC activate
It's gonna
the
go more than that, it goes to that point, but it must go further than that.
oh yeah, sure. Sorry. To this point, and just cross, turn on the light, and
All right. He also wants to know, that he says there is something missing on your diagram. Based on the PLC outputs.
okay. From the PLC outputs, something missing. Okay. So this is the source of my voltage. This is the positive, the negative. Yes, positive, negative. So maybe you can check. Yes. This is the positive, the negative, to feed for voltage to my PLC, and then the PLC provide the positive signals or negative signals. So
You sitting here, you're missing a common terminal for PLC outputs.
common terminal
PLC outputs.
for PLC outputs. Okay, well, this is the common terminal. Of course, we can have another commons that is located in the real PLC, is located in this side, but in the previous, I removed this connection to this connection because it's the same common, and just to do an easy way to understand the wiring diagram. Well, maybe Mr. Brock refers that this common needs to be here, and again rewire and with another wire from here to here.
Okay. I'm waiting for his response, but we're kind of running out of time here. Anybody else have anything else?
Yeah, at the start of your presentation, you kind of mentioned you had problems with wire sizes and things like that. What exactly were your issues that you had with wires?
Okay, no wire size. When I was using this type of connectors, I press the wire with a special tool, and that tool cut the wire internally of the insulation. So that's why I couldn't realize that that we don't have. So I put the wires, and I didn't know until I test several times what could happen. And that's happened with all my sensor levels. And this was only at the end, at the last day, that issue comes to me. Well, fortunately, I was able to solve that problem properly and on time.
Did you know why it cut the wire? Was it the wrong size of connectors, or was it the tool that you were using?
The tool, it was the tool, or maybe I didn't know how to use the tool properly, but the tool cut all my wires, and I didn't know, because they press.
Some crimp tools have different sizes on them.
Yes, I use the same color, I use the proper color, but that tool was
So is it a ratcheting tool or just a?
just the
No, but did it have a ratchet? Like, you got to kick it?
yeah, that way.
Well, then it was set wrong.
Yes, and cut all my sensors.
Just to clarify the previous question there, Mr. Brown says that's not how that's supposed to be connected. He actually is paralleling two power supplies, the DC sensor supply and the external supply. All right, so you might want to look into that. Okay.
Okay.
All right, I think that's all we have for time.
Yeah.
Thank you.
Thanks, John.
Okay,
Don't anybody leave yet? I'm gonna take attendance. Is Jed here? Louis? Yeah, Louis? Amrapelli?
Present.
Ashley? Aljon? Alejandro? Arpit? Here. Kubir, oh, sorry, no. Haley? Juan? Well, it's not here right now. Jake? Sean? Guillermo? Giovanni? Here. Kagandi? Marianne? Maricel? Johnson? All right. I didn't name you, I saw you and marked you down.
Help you out, brother.
Yeah, we'll see. As long as I don't jump in the word.
Jonathan, this is really good. All the way, this is super. Good job.
Maybe their own program.
But everybody's gonna like something else, right? That's the thing. I hate mine. That's why I spent so long building it. This looks really good. I like the one. This is not a problem.
Yeah, again, I want to.
Same thing, right?
Just don't want it in my
Best I can, but I like that your condos even have. I like that your condos even have patterns in the back.
Took my headphones off and put that. Some greasy ears. We touched it.
Good, thank you.
Phil's got shit.
Just gotta back it up with some words.
You don't need it, man. You got
I have to hear music from this side. Because these guys are
I should say the
my wife,
What is it?
1624, if you were cutting it. Did you use it?
yes, at the end, yes. Well,
I don't want to have a competition with scales.
Well, it has a 22 to 16 and 16 to 20.
The scale is 16. That's what he's doing.
It depends if it's not, let's say, the right crimp tool for the crimpers either, right?
Right. To get the right count.
Maybe it's like a crypto tool. Maybe the NBCC context.
I don't have a slide for the main tool, just the,
I picked phone for context.
How you feeling? Everybody's coming in. Thanks, man. Mine's bigger. Should I keep it unlocked?
No. Lock them out.
I was nervous that I was gonna forget it and people were just gonna start coming in.
It's not acceptable.
Not acceptable.
Not during your presentation.
Justin?
Thank you.
Confident?
Yeah. I'm trying to convince myself. Thank you.
Looking sharp? Good.
That full screen.
You know, Davis, that. It's not even tells me about the project. It's here to sell it.
Almost.
Yeah.
So my introduction's pretty much gonna sound like
Yeah, you're just missing the briefcase, man. You have that.
Where were you? Well, that's why I tend to stay in here. Okay?
Our next presenter's ready to go. It's Justin Cormier with his digital kitchen scale.
Thank you. So, good morning, everyone. My name is Justin Cormier. I'm an electronic engineering technology student here at NBCC, and I'm here to present you on my final project, the digital kitchen scale. So the purpose of my project, or the device that I designed, is to measure the weight of food and to easily display it to the user on an LCD, and to display it in either grams or in ounces. This benefits people different ways. One of the benefits is to help people control their consumption. So a lot of people have dietary restrictions or are trying to achieve fitness goals, and this type of device can definitely help them achieve those goals. Another thing is consistency. Consistency in the kitchen. Let's say you got a recipe that you want to recreate. You got a famous muffin recipe or cupcake recipe, and you want to recreate it. A good way to do it is to measure ingredients and to consistently use the same ingredients to consistently have good results. Another benefit is to control cost, especially in a kitchen or in a restaurant. So as a teenager, I used to work at a restaurant. The first thing we would do in the morning while prepping is to measure out portions for the day for the cooks and chefs to prepare throughout the day, and that was done to control cost. Because food is purchased by weight. To make sure that the kitchen turns a profit at the end of the day, you have to control how much food you're putting on every plate. And the reason why I wanted to do this project was actually in one of Metcalf's embedded systems classes. He had mentioned a load cell. And like many things, the first time I heard load cell, I didn't know what it was. So I had to Google it, and once I figured out what it was, I thought it would be a good idea to do my final project using a load cell and a microcontroller. So I got it approved, and here I am today. So the topics I want to go over throughout this presentation, I want to take a look at the functional overview, where I'll go over how a user would interact with the device, look at the block diagram, the flowchart for the code, we'll look at the technical overview, we'll look at the schematic, we'll see the components used in this device, we'll look at the PCB design, so my adventures on designing my first PCB, testing and results, a conclusion, and a quick little demonstration. Let's get my laser pointer. So this is the concept drawing for my project, so for the digital kitchen scale. To turn on the device, the rocker switch is located on the side of the enclosure. You put it on the on position, and the LCD will turn on, displaying the software's name and the version number. And once the device is turned on, the device will display the weight in grams. So if you want to convert that to ounces, you just need to press the unit button here on the right. And to tear the scale, so to zero out the value on the LCD, you can press the tear button here, which I forgot to mention here. If you want to actually weigh something, you got to put it on the platform of the scale, which is here and here. And the device is powered by a 9-volt battery, which is located inside the enclosure, but you can access it with the door located on the bottom of the device. So now we'll look at the block diagram. So like I mentioned, the device is powered with a 9-volt battery. It's got a fuse to protect the wires inside the device. There's an on and off switch to turn on and off the device. And there's a 5-volt voltage regulator used to supply 5 volts to the other components inside the device around the circuit. So the first component I'll mention is the load cell, which is the transducer used in this project. So it outputs a voltage signal when force is applied on it. So this signal is quite small, so it doesn't need to be amplified. So there's an analog signal amplifier located right after. But first I have a signal trimming pot. So I was having issues during my prototyping. An ideal load cell would have 0-volt output if there's no weight applied on it. And I was having like 1 millivolt outputting with 0 weight on the load cell. So I implemented a trimming pod to adjust it to 0 when there's no weight on the load cell. There's a gain adjustment potentiometer to adjust the gain of the amplifier. And there's a reference voltage adjustment potentiometer to adjust to offset the output voltage of the instrumental amplifier, which we'll see more in detail when I review the schematic. So the analog signal amplifier is connected to the microcontroller. So the microcontroller that I am using is the ATmega 168P. So it has a 10-bit ADC, so that output voltage from the amplifier is connected to that analog to digital converter. So that converts the analog voltage into a digital value that can then be used in the software to convert it into a measuring unit that we can read on the LCD display. We got the tare function and the weight unit selection button also connected to the microcontroller, allowing the user to tear the scale, tear the value that's displayed on the LCD display, or to convert the unit type from grams to ounces or ounces to grams. And this is all sent to the LCD display. Next, I'll show the flowchart for the codes. It's an embedded system, so there's a program. I'll just show the flowchart. So once the program starts, a splash screen is displayed on the LCD. So just the software name, version number. I'm missing a box here, but the ADC conversion happens between the splash screen and the tare, and tare is actually equal to the ADC conversion. So basically, taking the value from the ADC variable and storing it in the tare variable. After that, this is the main loop of the program, or the start of the main loop. So it starts with an ADC conversion, and the software checks, or the program checks if tare is pressed. Let's say the device is just turned on, the answer would be no, but weight is equal to the ADC variable minus the tare variable, and the tare variable was stored before this main loop happened. So that's what causes the scale to display 0 once the device is turned on. If the tare button is pressed, again the ADC value is stored in the tare variable. And then the program checks if what unit of measurement it's in. So if the device has just been turned on, it's currently in grams. So it would display the weight in grams. If it's been converted to ounces, then the unit type is obviously ounces. It converts the weight to ounces, and that's displayed on the LCD. So this is the main loop, and this repeats until the device is turned off. So now we'll move on to the schematic. So the device, again, powered by a 9-volt battery. There's a 800 milliamp fuse, which I sized based off the smallest gauge wire that I have in my device, which is 30 gauge, which I looked up is rated for 860 milliamps. There's an on and off switch, so once the switch is turned on or in the on position, it allows current to flow through the circuit, turning it on. The voltage regulator used as a linear voltage regulator is the LM340T5. It's a 5 volt linear voltage regulator, so you've got 5 volts at the output. There's 2 capacitors located at the input and one at the output. So the input is to prevent oscillation, and it's placed close to the input pin on the actual PCB. And then on the output, so C2 here is for transient response, so to phrasing here, transient response to if I remember, I'll get back to it. There's a diode here to protect the voltage regulator, and we'll go on to the next here. So the output voltage from the voltage regulator there is supplied to the other components of the schematic. So the first one, again, the load cell. So the load cell being used is the TAL220B. It's a beam type load cell. And when force or weight is applied on the load cell, there's a differential output voltage between the positive signal and the negative signal. So as more weight is applied, this differential voltage is increases. And the INA122P, which is the instrumental amplifier used in this circuit, which is basically a differential amplifier. This is why it's being used. It outputs the differential voltage from the load cell at pin 6 here. So the gain can be adjusted using this potentiometer here, R2. So according to the data sheet, a resistance value of around 200 ohms should be used for a gain of 1,000, which is what I'm using here in this circuit. Since the maximum output voltage from this load cell is 5 millivolts, and the reference voltage that I'm using in my program is 5 volts. So I just want to increase that to try to get that to 5 volts. The INA here is being operated in a single supply, so just the 5 volts. So the minimum output voltage at pin 6 here is 100 millivolts, and then the maximum output is 4.9. The issue I had during prototyping is when I was applying weight that was less than 100 grams, I wasn't getting any change at the output voltage here. So I put another pot here to apply 100 millivolt at the reference pin. So basically a voltage divider, and I can adjust it to get 100 millivolts to offset the output of 100 millivolts. Thus, when I put a small amount of weight on the load cell, an output difference is seen. So the output of the instrumental amplifier is connected to the microcontroller here, so to the ADC. So yeah, I'm using the 80 mega 168P, it's got a 10-bit ADC. I've got it connected to channel 5, which I'm just using because it was closer. When I was designing the PCB, that pin was closest to the instrumental amplifier. The push buttons are connected to PB1 and PB2. I'm using the internal pull-ups of the 80 mega 168. So if the push buttons are not pressed, you would read a voltage of 5 volts here on each pin, and once the button is pressed, the pin becomes connected to ground, which signals the program that the push button was pressed, and then the program either tears it or converts the unit type. I've got the pins here for in-circuit programming, so I can program the microcontroller right off the board. So since I'm also using the ADC, I gotta mention here that I'm using the 5 volt has to be connected to NBCC, and a capacitor here at AREF was mentioned in the data sheet to be placed at that pin when using the ADC for better noise performance. And that capacitor, that second capacitor at the output of that voltage regulator, it's for stability. So the LCD display, so it's a 16 by 2 LCD display, is connected to the microcontroller. So it's connected via parallel communication. So I got my 4 data pins connected to the microcontroller. I've got this resistor here, the 200 ohm resistor, is a current limiting resistor to protect the backlight LED of the LCD. These 2 resistors here is basically just to set the contrast. Instead of having a potentiometer to adjust the contrast, I just opted to find the ratio that I wanted and put 2 resistors. So the PCB design. So this was the first time designing a PCB. So my design was basically based off my enclosure. I knew where all my inputs and outputs were going to be, and my load cell was going to be located in the back here. My push buttons maybe in the front. My LCD was going to be located right around this area here, and my on and off switch located in the rear. Luckily for me, my enclosure had standoffs already for my PCB, so I already knew somewhat the dimension that my PCB was going to be. So 6 centimeters by 8 centimeters. And this is what it looks like. So the PCB was manufactured here at NBCC. So it's a 2-layer board. The one on the left is, or the figure on the left here is the bottom of the PCB, or the bottom layer. Top layer is on the right. So they're all through-hole components. So all the components lay flat on the top layer here. And the top layer also has a ground plane. So all my traces are on the bottom, and most of my pads too are on the bottom, so it made it easy to solder all my components. To electrically connect both layers, since both layers are not electrically connected, the vias with these pads here after they were drilled, a small piece of wire was placed in the hole and soldered on both sides to connect both planes. So this is what the final PCB looks like. So you can see all my connectors are located around the PCB, making it easy to connect and disconnect. So I got my LCD, my 2 push buttons, my battery, and my load cell here. This is for my on and off switch, but it had to be disconnected to take a picture. So the cost of the project. So the actual cost was $146.05. I had estimated $240 for the total project. It's not because I'm good at shopping for parts or anything like that. I just ended up saving money because I manufactured the PCB here, which I had estimated. I had added that cost in my estimated value, and my enclosure also changed from my designing phase to my actual buying the components phase, because the enclosure that I originally picked out was no longer available. So now for testing and results. So before I go, I start explaining my test. I'm just going to mention that the maximum weight that I weighed for this test was 2.3 kilograms, even though the load cell is rated for 5 kilograms. I noticed that when I was applying around 2,800 grams, so 2.8 kilograms to the platform of my device, that it was basically bottoming out the platform on the top of the enclosure. And this is due because for some reason it's the fastener holding the load cell is kind of flexing when there's too much weight, so I would have to reinforce the bottom of my enclosure or find an enclosure with a sturdier material or a material that doesn't flex as much. So the first test I did was I called it a consistency test, but it's really to test the accuracy of the scale and to see if that accuracy holds throughout multiple readings. So this was all done in one. I turned on the device once, I didn't turn the device off during the testing, and I tested from lightest to heaviest and would mark down my weights in the table. So another scale was used to actually measure the actual weight, so that I'm comparing my weight to the actual weight that I'm putting on my device. So there was 5 samples taken, and the average was then compared to the weight that was measured on the other scale that was used. So this gave me an error percentage, so it was low, which I was happy with. So the scale was pretty accurate. The next one was called the tearing and unit conversion test. So I wanted to test to see if I tear a weight off the scale and if I add another weight, if it affects the measurement of that second weight placed. So I wanted to see if the tearing was working properly. And I also wanted to see if the conversion was accurate as well. So I got two tables. I did this in grams and in ounces. So again, these weights were weighed on another scale. So these weights were placed on the digital kitchen scale and teared. And these weights were added. And then the actual weight measured on my digital scale was then inserted in the table, and these two values were compared, giving me an error percentage, which again was low. So I did this again in ounces, but I made a big mistake when I was taking the measurements. I had the other scale in fluid ounces and not in ounces. They're not the same thing. Fluid ounces are less than ounces. I didn't notice that there was a little drop on the scale. So I had it in fluid ounces. I took all the data. I anticipated that the error percentage was going to be higher. Not that high, but I just took the information, put it in the table, put it in this PowerPoint, and then last week when I was looking at it, I was trying to figure out why the error percentage was this high. So I recalculated it, but unfortunately I can't update this table. But the error percentage, because these weights here in the ounces, in fluid ounces, are actually higher, which decreases the error percentage. So my error percentage was varying between 0.4 and 2%. So in conclusion, I'd like to thank my advisor, Mr. Legier, the other instructors that sat in, especially during those EDRs, to keep me on track, to give me some advice to make sure I can finish this project on time. Thank you guys. Thank you to my classmates as well for all the help, for helping me complete this project. And so yeah, I completed a device that can be useful to help people control what they consume, and can also be used as a device to help control cost as well. I do have some future considerations though for my projects, things that I would like to see implemented. The first thing, I would like to fix the issue with not being able to read the full 5 kilograms, or in this case it would be 4.8 kilograms. So I'd like to fix that for sure. I would also like to possibly add a larger ADC, so a 12-bit ADC instead of a 10-bit that I'm using from the 18 mega 168. So that would improve the precision of the scale by quite a bit. So instead of having the least significant bit be 4.88 millivolts, it would be 1.2, which would be a lot more precise. And I would also like to add a rechargeable battery, since I'm just using 9-volt batteries. And since the voltage regulator I'm using won't regulate at 5 volts if the input's not at least 7.5, I feel like I'll be using a lot of batteries. So I'd like to implement a rechargeable battery. So that is it. Thank you. I'll be showing you a quick little demonstration of my device. So I got my little calibrated weights there. I got to return to the lab there. Right. So just show you guys how it works. So to turn the device on, like I said, the rocker switch is located on the side of the device. So it zeroes out when it's turned on. So right now I'm applying we're putting on 200 grams and 400 grams. So the device gets 400.4 grams. If you wanted to convert that to ounces, you can do so by pressing the push button, convert it back to grams. So to tare, just press the tare button here. Just add more weight. At 200 grams. It's fine. So when you remove the weight, it will display the amount that was tared on the screen, so in minus, so negative around 400 grams. And also when the device is turned on, just to show that the scale actually tears the weight when the device is turned on. And it's moved. See the amount? Just another feature I forgot to say, I got some bumpers on the bottom of the device for two reasons. My kitchen counter is pretty slick, so this helps keeping the device, give traction to the device. And if there's any spillage, I tend to make a mess in the kitchen. It's a nice little, not a foolproof protection, but I mean, it helps clean it up when you spill something next to the device. So that's my presentation.
Could you, bring up your schematic? But just before we go to that, I wish you could have shown a little bit of code too, being that that's a pretty big core part. And in fact, because I'm going to ask you a question on code. Did you do the math? Like there's converting, you know, did you do the math in float or integer?
The math was done actually in doubles.
So doubles is what? Float? Integer?
It's a float.
Okay, so can you tell me a possible problem with doing the math in float?
Possible problem with doing the math in float.
I'll be honest, if I was doing that project, everything would have been integer. So, float's bad.
Yeah.
So what's the reason float's bad? Remember?
I do, I'm trying to remember.
In integer,
Yeah.
if you have a, I don't know, 16-bit variable,
Yeah.
exactly how many correct values can you express?
How many correct values?
Correct values. If you do math in it, how many correct values can you express?
I'm not sure if I understand.
You have a 16-bit variable.
Okay.
You perform a math function on it, an integer math function. How many correct values? Doesn't matter what the functions are, doesn't matter what the original numbers are. How many answers, correct answers, can you get?
Or
Was it one?
representation?
Sure,
Maybe.
sure, maybe.
Was it one?
no.
Yeah, one correct.
How many
answer.
digital representations are there for a 16-bit value?
Oh,
2 to the,
2 to the 16, yeah.
exactly, no more, no less, right?
True, yes.
In a float representation,
Um,
when you're performing float operations, can you express every possible result?
no,
Why not?
there's just not enough bits to express it.
Yeah, but it's the format they're using doesn't allow you to
Mhm.
express all the possible values, and therefore it either rounds off,
Yes, yeah.
and when we round off, what happens? We get errors. So every time you're doing a calculation here, you're hedging your bets on you're gonna get a correct answer.
Which increases the
There's
error.
not. There's a very big distinct factor, right? Like, you know, things like comparing, for example, never compare floats. Never ever compare floats, because you'll never get the answer. Well, you will, but once in a while.
Yeah.
So I was just, again, curious. So if I were you, in a future version, I would sit there and do it. Okay. Okay, yeah, let's go to your schematic.
Was there a certain section of the schematic?
D1.
The
Are you
protection.
all asked, or-
I'll go for it.
You're all asked it here too?
Okay, so so that was to protect, I guess, there too, yeah.
So-
And I didn't go for, okay,
So what's it protecting and
How?
how and why?
okay. So the voltage regulator used here, it doesn't sink current here at the output, or can damage the voltage regulator if current goes in the output. And this can occur if let me get the,
What condition necessitates that D1 has to be
if there'd be a short on the input.
there? Well, oh, yeah, okay, yeah. But that's,
Because I was thinking, like, if there's a short at the input, since this capacitor here is charged, it'll want to
What's-
discharge.
well, what's the condition then? What's the general condition then? You're
Oh, okay, if the voltage is greater at the output than it is at the
Yeah,
input.
that would try to force current through U2, which it will not, doesn't want that at all, right? So what does the diode do?
What gives a path to the current to
Yeah, well, sure, but what's the result of that? That's saving U2.
the result of that saving into.
What can the voltage never be more at the output versus the input with U2 or a D1 being there?
0.7.
There you go, which is all within the range.
Yeah,
Do all voltage regulators need that?
the ones that I've seen, yes. Actually, these, I think I looked at a switching. No, the one that I looked also had a.
No, they don't always need to. You have to look at the.
The sum
manufacturer
can.
data sheet. Sure, some can handle that. That's not a big problem. A lot of people put them in when they don't have to. They just do it as a general, well, there's a 3-pin regulator, I'll put it in. But when you're gonna build a million of your scales, you didn't need to, right?
Yeah,
Okay.
I'm saving money on that.
That's right, right. All right. Anybody else for this one?
Not this part.
No. We should go to the next slide, I guess.
So further down the,
Yeah, that's, I got a quick question. Could you tell me what R2 is?
what R2 is?
Yeah,
It's a potentiometer.
you sure? Is it configured as a potentiometer?
No,
What's the difference between R2, R1, and R3?
this one's tied. It's a,
It acts as a what? If you can't remember the name, it acts as a what right there?
as a variable resistor?
Okay. Does R3 act as a variable resistor?
No.
No. It acts as a what?
As a potentiometer?
Yeah, but meaning what then? It acts as a what? What does a potentiometer do? The rheostat doesn't do.
And I'm gonna say, I think you said it earlier during the presentation, if I remember right, so think back to what you said.
That's a voltage divider.
There you go. So potentiometer is a voltage divider,
Yes.
where a rheostat is a
Variable resistor.
So one divides the voltage up, right?
Yes. And
The other one,
adjusts, varies the resistance of the.
so therefore it limits. Limits what? What does a resistor do in this circuit?
limits current.
Current, there you go. One's a current limiting device, the other one's a voltage altering device.
Alter.
Okay, very important, current, right?
Yes.
I'm playing with the big boys. Okay?
Yeah.
Anything else?
Not for this one, the next one.
Go to the next one. I actually I would have really liked that U1 there. You would have had a symbol that had the internals of it.
So the
So
two
we could have talked about it and seen it, yeah. Because I'm finding this year there's a very big lack of that. Because they're not going into the ICs to explain what's going on there, okay? And just having a box with these pins is really difficult to understand, okay? And
Yeah, sure.
Yeah, so here, on your LCD1 connection, the pin 15 LED plus, do you need a resistor there?
15 plus.
Yeah, LED plus. Would you need a resistor for that pin?
Not that I recall, no. But since you're asking.
Why or why not?
So 50.
What's connected there?
Oh, 50, oh, sorry, no, it is connected to a resistor.
oh, his pins.
Yeah,
oh,
no, I'm
don't
sorry.
do
No, no,
that.
no.
No, his
Okay, I
pins
see.
are not one to one. Oh, don't ever do that. Oh yeah, that is so confusing.
Yeah.
Yeah. You can move pins around, but you gotta keep the match.
Right.
Okay, you can move the pins around, but you gotta keep the match, yeah. Ooh,
That explains it.
that's a danger for a bad PCB design. Wow. Yeah. Cause I was like you, I was like, wait, how come there's, cause I remember you mentioning R7 there, but then
Yeah.
things didn't get.
I know some LCDs have built-in current limiting resistors, so I need to know if you need one or not. But it's just the pin I want.
I didn't know that some did, but I didn't know this one.
Not all of them. Not all of them.
Okay.
So I've got a follow-up question though. You said R5 and R6 are fixed value resistors that were placed there to replace a potentiometer, which is very common to do. But what I don't understand is the potentiometer would have one single output that is the voltage being divided with reference to ground. And in your case, you've got two resistors that go to two different pins. So basically, you substitute out a two output.
Instead of just a one.
Yeah, I don't understand that. Do you know where I'm going with this?
I know what you're going with this.
Like, I compliment you in saying that's why I use the potentiometer, because these things, that's how you're supposed to do. You're supposed to design them, find what the values are, and then trash the potentiometer, because you never change it again. It makes it a lot cheaper design, right? But because everybody sees it in the data sheet that it's, oh, there's a potentiometer, so I have that, they do that. But the reality for me is that you have a circuit here that should go from VCC to ground with a potentiometer swipe arm coming up in, but now you've got two resistors coming from ground, going to two pins that, you know, again, one is going to VSS to ground, so that's coming from the supply, but the other one, number 2, is going to VDD, which,
That's the same thing going on.
That's
Yeah,
wrong.
because they're only one.
yeah.
Yeah.
You just notice.
No, but it's still, you know, even when I track that, it still doesn't make any sense to me there, like electrically there. Like, I think there's something wrong there.
Okay.
Okay.
I think like I just basically had it down on my breadboard and I must have.
Well, maybe, yeah. Anyway, for me, what you have there does not replace a potentiometer, so, you know, so there's something not right there. Can you just bring back for a second, unless anybody else said something? Can you bring back just your general schematic for a second there? Oh, well, not the schematic, what's another drawing you had, that a mechanical drawing or?
Yeah, sure. So the mechanical drawing?
Sure, anything, I'm sure some of your other drawings will have, point out there. Oh, that one. So the scale of this drawing is what?
This one here was 1 to 1.15.
1 to 1.5?
Yeah.
If you were outsourcing that to me, I'd take the raw material and beat you over the head with it. Okay, who scales to 1 to 1.5?
I wanted to make it fit on the.
Who scales to 1 to 1.5, okay?
If it was too small if I did, then it was.
Well, yeah, 1 to 2 would probably fit, just so that play with the dimensions of it. Okay, just, you gotta realize this goes to other people too, and nobody scales to 1 to 1.5. At least it's a roundish number, it's not like 1.785.832, okay, or something like that.
Yeah, I had a different,
But
I thought I was doing better by going to 1 to
yeah.
1.15.
I think if you'd gone to 1 to 2, obviously it would have been actually a little smaller, but you might have been better off in the grand scheme.
I could have probably fit more.
Yeah,
I
I noticed and I was like, oh my god, I don't want to have to deal with that. Just all your calculations will go.
Thank you for.
Can you show me the picture of your PCB? Okay, so great picture.
A little fuzzy on the.
Yeah, a little fuzzy, great. But one comment for me is clean your flux. Okay, clean your flux. Every day it stays there. It's harder and harder to clean, and it's corrosive. It's going to eat at your board.
I tried to do most of it at home, but it wasn't.
How long did you take to try to remove it?
Well, I didn't have the. I just had like a toothbrush at home, so I was trying to get it out. But I didn't have the. Like we have here at the lab, like the compressed air to actually.
You don't need compressed air. Compressed air just accelerates the alcohol from evaporating. What people don't understand is the flux, the alcohol suspends the flux, but when you blow the compressed air, it evaporates the alcohol and the flux just sits right back down where it's at.
Okay.
You need to take the flux and the alcohol and whip it off, brush it off to the edges. Okay? The only thing you use compressed air for is when it gets underneath things, try to blow it out a little bit.
Look underneath the.
Okay, yeah. So, you know what, for me, a board like that, 20 minutes, half an hour before I'm satisfied that. That thing must be sticky. And it's going to collect all this dust and food particles and everything you're going to weigh is going to be, contaminated, salmonella and all that. So, clean your board, okay? It's important. In the long run, it's going to build this corrosive stuff, and it's going to short out or, open. Besides that, it's bored.
Yeah, I was happy with the way that it.
I hear the people that run that board house are pretty friendly, eh?
I got it pretty quick too, so it was.
At times. I had a question regarding the PCB, so I'm gonna quote you here, you said most pads are on the bottom. Are you missing pads on the top layer?
If I'm missing pads on the top layer, no.
They're on both.
They're on both, yeah. But the pads that I wanted to solder on, that's what I meant. So the pads that I'm soldering, actually making the solder connection to.
Well, you should try to solder every pad, whether it's, like, all the pads on top that aren't soldered should be soldered too.
Okay. Except the ones that I obviously can't get.
So, well, the ones you can't get, that's right. And then you clean your flux up.
And that's right.
Can you bring your tests up?
Yes.
I'll give you a question from Mr. Broad after.
Yes.
My only comment for tests, great tests, well appropriate for the only thing is your errors, you should have positive or negative errors.
Not absolutely.
No, absolutely, yeah. It makes a big difference in how you interpret that. It tells me a little bit of linearity results, right?
Okay.
Okay, so is it always you know, on the positive side is always on the negative side, right? Okay, and I don't think this one was too bad there, but the next one.
Yeah, the other one, no,
Yeah,
yeah.
definitely. So it tells me how linear the errors are, and then you can kind of, at that point say, why is that not linear, you know?
Well, actually, yes, stand up.
Mr. Wright had a question here. He said that you alluded to the fact that you use up a lot of batteries. How could you design things that would reduce the current draw and increase your battery life?
It's
How
not,
would, how would you change your design to?
well, it's not really to, yeah, I might have misspoke there. So is what the end during my conclusion when I said I would rather have a rechargeable battery.
Okay. But
So
even that will suffer the fact that it's, if you draw a lot of current, it's gonna.
yeah, but I mostly want the rechargeable battery so I don't have to keep purchasing.
Yeah,
manual
but
batteries.
still, that doesn't fix your, if you draw a lot of current, you draw a lot of current.
Yeah, this
Like,
device.
so how, what could you do to your device? What's a few things you do to diminish current draw?
Diminish current draw.
Yeah.
In my device.
What about your display? What did you do with your display?
Oh, I would turn the backlight LED off or.
That might be a reason there, the fact that you're probably running it full backlight.
Yeah, it's pretty great.
But that's one thing you can do. What else did you do? So you could, yeah, bring the backlight on the display. Control it's on, yeah. What about your micro? Did you do something to that? And it's sitting there doing nothing there. If you had it on right now, doing nothing there.
Put it to sleep or, yes.
Put it to sleep. Put it to sleep. Shut some stuff down. Right? Even when it's just needs to display, you can shut everything else off and just let it show the display. Or, you know what I mean? And only make it work when it has to work. If it's just sitting there chugging away all the time.
Strong.
Yeah. I would detect it too, right? So you could go to sleep, and then you change your weight or something. Turn the LED on, the backlight, right? There's all kinds of things you do with that. Okay? That's for phase 2.
Yeah, it was.
Oh, you also said that when you answer there, the short at the input, the F1 is a short always, so it was a good answer. Remember, he said that if the input is shorted, you know,
Yeah.
F1 is always a short.
Yeah.
All right, I think that's it.
Yeah.
Thank you.
Thank you.
Yeah, well, because I didn't spend time like how long. Yeah, so they had real time.
Oh, okay.
You need something?
Like this one. They started and he doesn't like it. So I think we'll have. Yeah. We also have to like respond to other notions. Yes.
Hello everyone. Here we have Mr. Lubani here with his active sonar with LabVIEW. Okay, you can take it.
Hello, ladies and gentlemen, dear instructors, friends, and family watching this transmission. My name is Juan Lopari, and today I'm going to present the topic Active Sonar with LabVIEW. Those are the contents that are going to be covered in my presentation. It's composed by introduction. We're going to see a bit of the concept design, the technical description, testing results, conclusion, and at the very end, demonstration of this work, of my device working. So, introduction. The name of the project is Active Sonar with LabVIEW, but what is an active sonar? Even though, why active? Regarding sonar, there are two kinds of technologies mainly. One is passive and the other is active. It's passive when, to detect the distance, it only receives the signal that is being sent, a sound wave, but it's active when it emits a sound wave and detects the time that it takes from since it was sent until it's received. So that's why it's an active sonar. The device that I use to develop my project is an ultrasonic sensor that's going to be shown here. And yep, this ultrasonic sensor is a 5 volts one that I'm going to cover more in the next slides. Also LabVIEW. LabVIEW is a powerful graphical programming environment, and I decided to use LabVIEW because I had some experience before. And I found in LabVIEW that it's, a difference to other programming environments. It's easier because somehow it's graphical, and since the scope of my project was to visualize my results into a plot, to be able to see it in a graphical way, LabVIEW will be a great fit for it. So let's start with the concept and user functions. This one is the concept drawing for my project. We can see that I have an ultrasonic sensor that is mounted on top of a servo motor. Servo motor cannot be seen, but it's inside. I also have two push buttons. Those are switch 1 and switch 2. And in the back, there is an FTDI cable that has a USB connection. Also, there are two LEDs. One is for the alarm, and the second one is to reflect when the device has power. So, yep, let's see a bit of the user functions and the initial conditions. As part of the initial conditions, we have to verify that switch 1 and switch 2 are released at the moment of connecting it. There is an important reason for it, but I will mention that in the testing part. Second, we need to open LabVIEW, and third, run the program. So in that way, we will be set to start working with this sensor. Switch 1 and switch 2. Switch 1 is the green, and it will select between sleep mode and run mode. If it's pressed, it will, the system will be in a run mode. But meanwhile, it's not pressed, it will be in sleep mode. And regarding switch 2, This one is only to control the rotation of the servo motor. I mean, if it's not pressed, the servo motor will be constantly rotating. Meanwhile, when it's pressed, it will stop the rotation, but the measurement will be still active. So I will only, since the sensor will be constantly doing this movement, in the moment that I press stop, it will keep fixed the ultrasonic sensor, but the measurement will not stop with it. Let's see the design. Well, the one that is shown now is the block diagram with the one I work with. In this block diagram, there are two main functions. The first one is to reflect how is this guy being powered. Regarding the power feed, it's USB powered by 5 volts. The entire power comes from this cable. Here I am taking 5 volts from the laptop, and it's gonna be connected to the random 3-volt switch. Then I have the ultrasonic sensor. The one I'm using has 4 pins. 2 of them for VCC and ground, and the other 2 are for receiving and emitting the signal. How this guy works? It has, as I mentioned before, this sonar has to emit a signal, so that's why it has a receiving pin. It will receive a trigger signal from the microcontroller, and after a period of time 10 microseconds, it will detect that signal coming back from any surface that was in front. And once this signal is detected, the pin 4, the transmitter, will emit that signal to the microcontroller. So let's talk about the microcontroller. The one that I'm using is the Atmega 328P. I connected in this way. There are 2 input switches, switch 1 and switch 2, that are those 2 guys are switch 1 and switch 2. Also, here is the USB power and communication. Pins 1 and pin 4 and 5 are for VCC and ground. Meanwhile, pins 2 and 3 are to determine the connection between the laptop and the microcontroller. So pins 2 and 3 are going to pins 2 and 3 of the Atmega. Also, the ultrasonic sensor is being connected here. On the other side, what I have are a visual and sound alarm, and this LED is the visual alarm, and this other one is the sound alarm. They are going to be activated if the value that is being measured is less than 50 centimeters. If while it's working, is there any object below the range of 50 centimeters, it will determine that the alarm must be on. The other one is the servo motor. This servo motor is controlled by PWM. It has 3 pins, one used for VCC, the other used for ground. And the one that is for PWM is connected to pin 12. Pin 12, for this Atmega 328P, for being able to handle PWM, there are some, not all the pins can do that function. So pin 12 is one that is capable of doing it. Also, here we can see J2. What J2 is for is because if by any chance, in the future, there is a need to update the program or to make some modifications, it can be done by connecting the picket to J2. Okay. Now we're going to see about the serial interface. My serial interface is the FTDI, and there are some good reasons for using it. It's not possible to connect a microcontroller directly to a laptop or a PC without using this FTDI because because it's the FTDI the one that implements this USB protocol stack. What this protocol does is it says to the laptop which ports being connected, what is the, if it requires some driver to handle that information, and also it will manage the data transaction between the laptop and the device, and the embedded device. In this case, the active sonar. Okay, our next block is the laptop. Here I have the program that is running in LabVIEW. It looks messy, but I'm going to explain it in detail, trying to associate them by functions. So the first function that I'm going to describe from this LabVIEW program is the serial communication. In this serial communication, what I have here is a communication port. So in the program, I need to say which communication port I'm using to connect the device. While doing the testing, we will see how is this changing. Also, regarding the serial communication, this one is established at 9600 bits per second. It has also 8 data bits, and there is non-parity bit for this connection. After setting this, there is a requirement to open a visa session for the serial communication. And inside the loop, the first thing I'm doing is I'm gathering the position I will gather I will read the variable of position, because in the way that I program the mega equivalent AD here is that the first value that it's going to send is the position, the second value that it's going to be sent is distance, and after that it will receive a value from the program that it's going to write a speed for the servo motor. So, and this can be the same or it can change, but that value will be written here. After that, I need to close the session until the next loop is done. So this is the way I'm gathering servo motor position. Once the value is written as a string, this value comes as a string, it's converted to a number, so now I can process it. But in order to get that 180 degrees, I am going from, in the program, is running a for loop between 9 to 30. So I am converting this small range from 9 to 30 until a range that can go from 0 to 180 degrees. The way of doing that after performing some calculations is multiplying the value received by 8.57 and subtracting by 1714. So after that, I have a value for my servo motor positions that is in degrees. The next thing I'm gathering is the distance. And so here again, I'm getting the information coming from the serial bus and converting this to a number and being stored here in this local variable, ultrasonic measure distance. So having those, what I can do now is the plotting. So the way I'm plotting is I am getting both values and storing into an array. From this array, that information is being sent to this polar plot, where it has some other details. Here, for example, these dimensions is set in 500, 500. Why 500? Since the range of my device is 2 meters and 50, let's say I am in the center, I will have 2 meters and 50 in this direction, and I will have 2 meters and 50 in that direction. But I'm working in centimeters, so it's 250 centimeters and 250 centimeters. So my diameter will be 500. That's why it says 500 and not 250. Same thing for the since I will be covering in this position, I will have a rating of 250 and a diameter of 500 for this circle. The way it's being shown in the plot is going to be as points and with the size of 20. I added some logical functions to this because I already have one alarm LED here in the device, but I also want to have a virtual LED that is going to be on the screen. And other than that, I have a condition that is out of range. This out of range condition is for any value that is being measured above 250 centimeters, 250 centimeters. So if, it's being compared by 500. This 500, there is not a real reason why it's 500. It could be any other value, but I'm picking 500 just because it's above 250. So what's going to happen? Let's say it measures 251. With 251, the program will send not value 251 to this to LabVIEW, it will send the value 500. And that value is going to be compared with my reference and then determine that the value, the LED that reflects my out of range condition is going to be on. Yep, and this one is for transferring the speed to the servo motor. So what I have here is a knob that it's gonna send that information to an array, and that array then being converted to a string, and that string being sent by the bus to the microcontroller. So that's the way it looks. I think it's gonna be easier to understand now since we know the models. The next part is how to display the angle and the position of the screen. So yep, this is the interface that I created for this application. What we can see here is that my communication port is, well, for the example I did, it's communication port 3. There is a value measured in centimeters, but it's also shown here. So this 239 is reflected here. I have the value in degrees, that is 103. And since this is 90, yeah, it should be right here. Also, this is the one that will allow me to change the speed of rotation. So my minimum speed rotation will be 1, and my maximum speed rotation will be 10. I can change those values since it's not something fixed. But yeah, this is like the way that I already programmed. This is the out of range LED that's going to be turned on. If the condition is that there is something measured above 500, and the virtual LED that will look like an alarm. So let's enter into the code. Well, for doing this program, what I did is I used several prototypes, several functions. Going in detail is I used one to initialize the PWM, another to initialize the communication. This one is for the ultrasonic sensor. Transmit byte and receive byte are the ones we used in class. Those were done by Mr. Nakov. Also, transmit position and transmit distance are two functions that are going to send those values to my software in LabVIEW. Variable speed and check distance. And this one is to perform the sleep mode. The interaction of the sleep mode. Yeah, how is the init PWM done? First, it was declared in the main void, and this one is the function that is being used for it. So what I'm doing is I'm setting the condition, the special function registers of COM081, WGM01, and WGM00. in this special register. And also I am prescaling this with CS00 and CS01 to a value of 64. This is necessary to do because the servo motor cannot run, its PWM cannot run at the same frequency of the omega, that is 12 MHz. So it must be prescaled, and then it will work. The next function I want to show is the communication one. So it was defined as 1 megahertz. Also, I defined it as 12, meaning that it is 9600 baud rate at 1 megahertz. This one comes from the datasheet, and initialize it in the main function. The communication was set as A bits, non-party, one-stop bit, with the function to transmit and receive bytes. Yep. So that's explaining this function. Regarding the testing results, I performed 2 different tests. The first one is to measure the accuracy. So what I did here is I keep the sonar in a fixed position, and from there I determine the first 1 to 3 centimeters. I used a box with known dimensions, and I place that box at different distances and try to determine what's the error of each measurement. So this one was at 3 centimeters, the second one was at 10, 25, 50, 1 meter, 1 meter and a half, and then, and so on. So the results of this first test were those. Here there's an error for the maximum because, here it's not applicable. Since I am measuring a value that is above 250, the value that I'm getting from the omega is 500 because of the programming. So this error it must be not applicable. Same thing with the other charts. But other than that, what I noticed from these results is that I have less error when the box is large. Meanwhile, when I am using a small box, my error is high. Another thing that I notice here is that when I am measuring close to the blind zone of the ultrasonic sensor, my error is also very, very high. So, yeah. This is the second test that I performed, is the power consumption test. It was done by connecting a USB-A multimeter and then plugging in 2 conditions, basically. One was sleep mode, and the second was in run mode. Also, in the run mode, I tried with the servo motor running at low speed, at medium speed, and its high speed. So the values were different, and the current consumption in each one of them was different. Those are the ones for sleep mode. Oh, sorry. Yeah. So for sleep mode, I got those values of measured current. There is something to notice here. The thing is that the USB multimeter that I used for it, the minimum value that we recognize is 0.05. So it's possible that my consumption is even less, but because of the limitation of the device that I used to measure it, I won't be able to know what's this value exactly. And when it was running to its maximum speed, yeah, I got those values that are considerably higher than meanwhile I am in sleep mode. Let's see some conclusions. Well, the active sonar with that view provides reliable distance measurement and flexibility for processing gathering data. Yeah, that margin of error that I got in my results are in absolute accordance with the technical description of the sensor that has a ±1 centimeter. Also, new skills development. Yeah, I mean, while doing the project, I enhanced my programming skills, and also, I mean, while doing PCB, each stage has faced different problems, different challenges, and happily I could avoid them on time. Some future improvements for this project are I would like to upgrade it to a wireless one. I mean, for now I'm conditioned to be using a wired connection, but yeah, it would be great to get this guy working as a wireless device, since I will need to change that. I mean, it will require some major change, because first it will need a power source, so it will be some batteries or maybe a power bank. Also, the communication cannot be the same that is being used here. Maybe it will be necessary to use some kind of Bluetooth or something similar. What could have been done differently? Yeah, I mean, something that I noticed when this was running, since the idea of this is getting a surveillance device, it's that the motor was quite noisy while running. You might notice that when we were doing the testing. And also the sensitivity is like not, I mean, it's going like from 8 degrees and then 8 degrees and then 8 degrees, not going like one by one. That would be my expectation. Those are my references, and thank you. Thank you guys. Sure. Let's do the test now. Thank you. From this point to there. Hasta 10. Okay. So the first thing we have to check here is that both buttons are not pressed, so both of them are released. Now I'm going to open the LabVIEW program. Okay, so now I have to connect the USB here. Let's take the program. So now I have to select which port was connected. In this case, was connected to COM3. And now I need to run the program. So next thing I'm gonna do, I'm gonna leave the sleep mode and start the run mode. Okay. So what he's doing now is detecting those objects. Yeah, but it wasn't impossible. Okay. Yeah. Right. So there is another condition when the alarm turns on is that when it's out of range, it also turns on. So I'm gonna stop this when it's in front of those boxes. Okay. So now it's detecting my hand. Okay. So yeah, there is a distance of 93 centimeters that is being read. Let's see what's getting. Okay. So it's detecting the presence of the table. Yeah. And also, maybe I need to. Okay, let's see. Okay. So now, come on. Okay, and when I performed this, it was all on the floor, so it was kind of easier. Now I cannot reach the floor because my cable is not long enough. But yeah, I mean, what I can do maybe, I will improvise a bit. So what I can do is, so now I am in the outrage condition, and since I will be approaching, it will be detecting my presence constantly, and every time I am below 50, okay. Yeah, now I am in the non-safe condition. Now it's out of range. So yeah, that's it for my demonstration.
Can you bring up your schematic? I'm going to be blasted away. Glad you. Can you describe to me how, well, first of all, switch 1, switch 2, physically, what kind of switches are they? What type of switches are they? I'm looking at your bill of materials for type of switch.
HBC, single pole, single throw.
Single pole, single throw?
Yeah.
Sure. So you click them one way, and they stay that way? And
Yeah.
so they're slided on or off? So they don't, it's not a push button switch?
No, it's not.
Okay. And that's because it engages certain modes, is that what that is?
I'm sorry, I didn't.
It engages certain modes.
It engages certain modes. It means that to keep.
Well,
that-
enables certain modes, so it's not when you turn a button on it, that mode you want that to stay like that, right?
Exactly, yeah.
So is it a slide switch? Is it something you slide over?
No, I pressed that.
You press the button and it locks down?
Yeah.
Okay.
That's-
All right, yeah, I was just wondering, because I wasn't sure if that was the right symbol or not. Also, it'd be nice that you would indicate what the switches are on your schematic, what they do. Okay, that's fine. So talk to me about that configuration of that switch in relationship to the input of the 328.
Yeah, they are in a configuration of pull down.
Pull down.
Yeah, because pins 4 and 10 are connected to ground if the switch is not pressed. So once the switch is pressed, it will send the one condition, one logical condition. But if by any chance it's not, it will give us a pull down.
Okay, so why did you suddenly pull down instead of traditionally you pull up?
And I think there is not like a reason in particular. Probably was, while doing the programming, since I wanted to get the condition done in the position of 1, working in not 0. So probably that's why. But other than that, I didn't do like second thoughts about it.
Okay, I'm just wondering because it's, typically when you pull down, there are reasons for it. That's fine. One of them is you want to be different. Anybody else with this schematic? Anything else for it? Or you can, could you bring up there's a picture you have of your, maybe it was the ultrasonic sensor.
This one?
No, not that one. Although I'd like to point out that one, the middle drawing is very confusing to me. I didn't understand the middle drawing because part of it's cut off there.
Oh, this one?
Yeah.
Yeah, that was a problem that I was facing since I picked this sensor because, I bought it from AliExpress.
No, I'm saying that your drawing
Oh, this
is
one?
confusing.
Oh, yeah.
No, the other one.
Oh.
4, 3, 2, 1. See how the bottom's cut off?
Oh,
So
yeah, you're right.
I was looking at it, didn't understand what that was represented. Anyways, I figured it out eventually.
No, I didn't realize this.
So keep going because it's not the slide I want to talk about.
Okay.
Oh, maybe it was the communication slide. There. So, a few questions here. So, number one, the connector you have there, not the USB one, but the other, and I use connector in quotes. What's a connector for?
Okay. Do you mean what are those for?
Yes.
Okay, so in one end I have a USB port connection, but that USB is composed by 4 wires. So those 4 wires are the 4 ones that
No,
are
I
here.
understand, but what in general do we use connectors for? What's the purpose of connectors? There's several purposes.
It's like to replace it easier.
Or to make it, to connect, disconnect, that's one purpose. What else? Let's say I was working on your device there and I disconnected your connector, and I want to plug it in again. What are the odds of me plugging it in correctly?
Okay.
You understand what I mean?
Yeah, I do. But
Like if one of those 2 wires, the green, look at the green and white wires, you can even see it on that drawing. They are aching to be flipped around so easily. They almost flip on the drawing, it's so much, right? And how would I know, oh, I flipped them around inadvertently, or? And what happens if I do flip them around? What happens if I flip ground and power around, for example?
Yeah, sure. Well, that was not exactly a problem, but I mean, I was
Could
being
be.
careful with
You're
that
careful,
particular
maybe the next
condition.
guy following up is not so careful.
Yeah, sure.
Or maybe he doesn't have the information. Is there anywhere in your documentation that tells us, you know, that it is here, but, you know, is there anywhere else where it tells us what the wires mean, what they're, 'cause if you tell me you flip red and black around, things are gonna go.
Oh, yeah.
So what could you have done instead of using that connector?
In my PCB, I'm using okay.
What could you have done instead of using that connector?
I probably use a connector that is not like this. I mean, just like one where the pins are fixed.
There you go.
With
'Cause note on the other side, on the USB connector, it only goes in one way.
Yeah.
You have to go 3 times to get it, but it only goes one way.
Yeah.
And you guys didn't know that? 1, 2, 3, right? Or every time. But there's absolutely no way you can put it in wrong. If you put it in wrong, you broke something. Right? But on your other side, that's not the case, right? So yeah, no, you should have went out and purchased an appropriate connector. And there are connectors that are that have the same pitch as the header pins, and you can even key them properly and everything. Okay, and they work a lot better than that. Bring over. So this takes the USART, turns it into USB because of FTDI. Go to your LabVIEW. And yeah, and then when the data comes into your LabVIEW, then it does what? It's USB.
Oh yeah. So right here's here. But what it does is here in the loop, it's done like by sequence. So the first bit that it's going to be received.
Oh, I understand that, but so it goes, it connects USB wise, but in honesty, it's actually still.
Oh, it's still bytes.
Still serial, right? Yeah, it's serial over USB for a portion of it. And then it's incorporated here, because as soon as you start talking about 9600 and no pair 8 bits, it's still in serial format, right? Yeah.
Oh,
Okay. All right. I don't know if anybody else has questions on LabVIEW. I tend to not want to deal with that.
Well, you might have the same question. You said you had an input value and then you converted to degrees. Where did you get those numbers? You had a multiplication of 8.57
okay.
minus 77.14, but you kind of just brushed over that.
Sure.
How does that convert?
Oh, no problem. Yeah. So, by experiencing during this SPL course, what I thought is that my servo motor, it runs from 0 to 180 degrees when I am assigning to that function register the value of 9, I am in this position. And when I am assigning a value of 30, I am in this position. So what I had to do is convert this range from 9 to 30 to a range that goes from 0 to 180. So it was 9 value equivalent to 0 degrees and 30 value equivalent to 180. So I define this relationship, and after that I go to those values. So that's how those numbers come out.
You're partway there.
Yeah.
There's more to it than that.
Yeah.
But that's what I do.
Well, how does the 77.14 relate to
Oh, okay.
that
So this is.
scaling?
Okay. Okay. I'm missing a piece of information. Oh my god, this is embarrassing. Just a second. So what I did was. Sorry, I'm just nervous. So,
Maybe we'll keep going then.
yeah.
Yeah.
I just one comment here.
Okay, sorry.
The lot view is not something that I profess to know very much about. In fact, I've gone out of my way not to have to deal with it. Okay, and I know that's, for some people, some people are with me, some people are against me with that, on that's, live and let live. But all I can say though is that even outside of that, one of the difficulties I have with LabVIEW is kind of wrapping my programming head around how the program goes sequence-wise and that, and comment-wise. And you even said that it's kind of messy. You're not helping anybody understand your work by doing that. And it's like any other. If you've done this in C, C++, it's really no excuse at all that you should have a nice layout there that's very understandable, almost flowchart-ish in nature, okay? And so that you can present that and people can see that. And because for me, that's the thing, that those numbers up there, 857, 74.14, I have no idea what those are, right? And it says bundle and build array, and those for me, they don't represent anything. You could add comments to this too, right? And make this clear, but you can also lay the flow better. Because the power, from what I understand of LabVIEW, is that it is visual, but it's visual again coming back to solving a problem, right? The tool to solve the problem. So we should be able to look at this and say, here's a system chart, flow chart that I can go through without your assistance to understand what's going on and say, yeah, I get it, And I don't feel like I can go through this and tell you exactly what's going on, to be honest, So, anyway. All right.
Thank you.
Half hour to 2
As always.
Great man.
This one?
Plus minus.
Maybe it's on the other side.
All right, everyone, so we'll pick up the presentations for this afternoon. We still have a couple presenters. We'll start off with Adam Brewer and his solar tracking versus fixed angle analysis project.
Good afternoon, everyone. Welcome to my senior project presentation. My name is Adam Brewer, and I'll be presenting my project, the solar tracking versus fixed angle analysis. This project is a comparison of two photovoltaic systems, the first being an active dual-axis tracking system, and the second being a fixed angle system. So the scope of this project will attempt to answer the following question. Is a sun tracking PV system worth the extra costs and complexities compared to a fixed angle PV system? This project attempted to answer this question by designing, building, and testing a model of a dual-axis tracking PV system, which includes a sensor for detecting the sun's position, and also a simple fixed angle system. I use these two systems to collect data on the power output of the two panels, and found the daily average energy outputs of the two systems. Then I used that data and compared the results and observations to come to a conclusion. So first, let's back up here and talk about PV system designs. So PV system designers have a lot of factors that impact the outputs of their systems, many of which they have no control over. But two things that PV system designers do have control over is the panel orientation in relation to the tilt angle from horizontal and the azimuth angle in relation to true south. They also have control over, in most situations, the shading impacts of the landscape or buildings surrounding it. So one method PV system designers can use to increase the amount of power their systems can output without increasing the number of panels is to implement a tracking method. So the purpose of a tracking method is to increase the power production of the panel, and how it does this is by keeping the panel more perpendicularly aligned as such right here. So the theory being that the more perpendicularly aligned the panel is to incoming solar radiation, the more insolation in watts per square meter it will hit that panel. Now this is just a simple visualization to understand what I'm talking about here, but you can see the misaligned panel here is not capturing as much over its surface area on both directional axes here. One study that I looked at found that a dual-axis tracking system output 30% more energy annually. So this is kind of the baseline for my system. I decided to conduct the testing at NBCC Moncton outside the Alternate Energy Lab, E1011. This site was specifically chosen because it was the only site I had access to with minimal shading impacts, a power source for the tracking components, as well as the equipment that's going to be responsible for data collection. Being on campus, I could also, during the daytime testing, be close by to make sure the system is functioning as properly, isn't being tampered with, and then I could also make observations on what the system was doing. As you can see here, this is my shading analysis for the site just outside E1011. So I set up for the month of May to do my data collection. So I was doing data collection during school hours from 8:30 till 4:30, and I was clear of obstructions from 8:30 until well past the end of the day here. So during the month of May here, I had no shading obstructions, so I thought this was a very good place to do my data collection. Next, we'll get into my functional block diagram, which is a system overview of all the components. So we'll start off here with the sun that interacts with three components of the system. The first component here is the fixed angle solar panel, which is known as PV panel 2 from in future slides. The second component is the solar sensor, which is powered by the auxiliary power source here, and that controls the XY motors for orientating the sun tracking panel here, which is the third component of the system that the sun interacts with. Each panel has their own series of resistors that are used for measuring voltage and current. Each have a dump load resistor, which is for the bulk voltage measurement of the system, and then has a shunt resistor in series with it, which is a very small resistance to get a very small voltage drop for a very accurate current interpretation. Both these are mirrored for each system, so they have their own data streams for each output. And as you can see here, they all lead to the DAC for 4 streams of data, which is then collected to a PC, which I use for analysis. Next, we'll do an overview here of the wiring diagram. As you can see here, the hash marks here is the inside E1011. I was lucky enough to have a power outlet right next to the window, so I could conduct my testing right outside E1011. We'll start here with the power source, the auxiliary power source. It's a 120 volt AC to 6 volts DC, 3 amp regulated AC DC wall adapter. It feeds into the PCB enclosure here. And then points of interest here, we have the terminal block J3 here. This is the terminal block for the sun sensor. The sun sensor is a LDR-based sensor, which is wired in a way that each axis is a series of LDRs, and both axes are wired in parallel, so it's a parallel series configuration. I'll get into this more when I talk about the sun sensor functionality with the window comparator functionality. Also can be seen here is the motor outputs from terminal block J2. They feed up here to the motors M1, which is responsible for the x-axis rotation, and M2, which is responsible for the y-axis rotation. Here is the PV panel connectivity here. We have the AWG 18 gauge wires from the PV panels spliced to AWG 10. Then they're connected to the dump load resistor through ring terminals and the shunt resistor through ring terminals. And then simple AWG wiring, AWG 18 wiring connects to the terminal blocks of the dump loads and the shunts to get 4 streams of data collection. There's also a series fuse here. This is to protect the shunt resistor, which is only rated for 5 amps. So here we have on the left-hand side here the system setup, actively collecting data. The tracking system is in the background here. It's tracking the sun, which is directly over my head from where I took the photo from. The fixed angle system is facing true south right now, and this is a picture of the setup. As you can see, the wires lead inside here to the 2 dump load resistors. So here's dump load resistor 1, here's dump load resistor 2, shunt resistor 1, and shunt resistor 2. The nominal resistance of the dump loads was set to 90 ohms, the lowest setting, and then each shunt resistor is 0.01 ohms. Then they feed the data to the DAC right here. These solar panels are both identical panels. They're ACO power 10 watt solar panels with a Vmax of 17.5 volts and a maximum current of 0.57 amps. Next we'll get on to the physical build here. We'll start here with the housing here, which is mounted to the frame, directly bolted to this frame here of the panel. This contains the connections for the LDR sensor. From there we have mounting brackets here made of 1x1 aluminum tubing with a 3/8 threaded rod fitted through it. I had to custom make this. I couldn't really source the tools to make something really good, so I was able to use a 3/8 threaded rod and the horizontal rod going through here with the timing belts on it. I was able to connect those with a cable clamp so that they would be secured. I used this 10-to-1 timing belt gearing here specifically because I was meant to use a larger solar panel, a larger 100-watt solar panel. I was really concerned about the torque capabilities while staying within the 6 volts of my motors. So I wanted to increase as much torque as I could, and I found that this timing belt would be a solution to that. However, many other issues with the x-axis bearings and the attachments of the solar panel made me reduce the panel size to a smaller panel to solve many of these issues. From these mounting brackets here, this is the 10-to-1 gear pulley right here. On there is coupled the M2 y-axis motor. The mounting plan that I had for this was to use a bracket that came out and could secure the motor to the frame. However, the bracket wouldn't fit with the collection of attachments I had here, and I also had to make the frame smaller for the smaller panel. So doing this, I lost space for the bracket, so I had to make a custom-made motor mount here. From there, the frame is a 1x1 aluminum tubing frame held together with L brackets here and bolts. It is resting on an x-axis bearing here, which is for a lazy Susan, or a rotating flat table that I found. I then used a 3/8 threaded rod connected to the bottom part of the frame here to connect motor M1 here. Now, I tried to do a 10-to-1 timing pulley for the x-axis as well. However, I wasn't able to get the alignment right. The alignment was crucial, and I found since gravity was a factor in the way it was set up, I kept getting misalignment due to the 3/8 thread rod not being perfectly straight, or the motor coupling coming loose. So I decided to directly couple to the 3/8 threaded rod, and I didn't have any issues through testing to get the panel to move the way as intended. So here we'll get into the sun sensor functionality. So as I mentioned before, this sensor here is wired in a series, or in a parallel series configuration, meaning that the y-axis and the x-axis are in parallel with each other, and across each axis is a series of LDRs. So these LDRs work like variable resistors in the sense that in the presence of light, they have less resistance, therefore permit more current, and in the absence of light, they have increased resistance, therefore less current. So this sensor here feeds an LM33N comparator. It is configured in a window comparator configuration. The window comparator configuration has each comparator set up in a in a non-inverting fashion, and the other set up in an inverting fashion. So here is the x-axis side of the circuit here. So for example, if the negative X LDR is shaded, here the V in will be compared against this VREF high value and this VREF low value, which can be adjusted by the RV1 here and the RV2. So here's a visualization of the window. This is the upper reference voltage here for 4 volts at 2/3 VCC, supply voltage. And here is the lower reference at 2 volts VCC supply voltage. So this window here, when the LDRs are balanced, it's a voltage divider, so when they're balanced, the difference in the voltage is 1/2 VCC, so the output would be right here in the middle at 3 volts. This gives a 2-volt window for the voltage divider to rise or fall before it sends a signal out of the comparator. So, for example here, if this negative X is shaded here, there will be the VREF, the V in value will rise above the VREF high value and output a high signal here. I'll show this a little bit more in detail in the coming slide here with the schematic. So here is the overall schematic here. I'll just make a few points here to note. Here's my power in right here through J1, which connects the switch. And then this is actually a 2-amp fuse I decided to reduce the size of. Here is the LDR sensor out block, J3. Here is the power pins of the LM33N comparator with a decoupling capacitor. So here we just saw on the previous slide there, this is the schematic view of the comparator circuitry for the x-axis. As you can see here, the V and X comes here. It's sent in through pins 7 and 4 here to the comparator, and reference against 2/3 VCC for VREF high and 1/3 VCC for VREF low. If there is a high output from this terminal here, from the V in X is greater than the VREF high, it will put out a high value here, and if it's lower, it will put a high value out of pin 2 here. When either one of these 2 pins are putting out a high signal here, it will forward bias these diodes here, which send out a signal here that goes to the enable pin of the motor driver. And then here is the circuit on the other side, completely mirrored the same way. The only difference here is just different pins, and this is for the y-axis here. So here, pins 9 and 10 are connected for V and Y, and then they output a high value if V in Y is greater than VREF high from pin 14. And then the same if it's less than VREF low, it outputs through pin 13. And again, both of these pins, when either one is outputting a high signal, it will bias either one of the diodes and output a high signal to the enable pin. Now this is the motor driver circuitry here. A few things to note here is, so here's the enable pin here, coming from either one of those diodes, D1 or D2. So that will enable when either one of these inputs are high output. This is the VREF high pin, so pin 1 goes to pin 2, pin 2 goes to pin 7 of this here. And then for the y-axis, this is the enable line here, so this is where the D11 or D12 will forward bias and activate the enable pin here. And then the for pin 14 for V and Y is greater than V ref high, it will output to pin 10, and then for V ref low to pin 15. Now this is the L293NE, so this is a model without internal clamping diodes. I chose this model specifically because it increased my power output per channel from 1.2 amps to 2 amps. So doing such, in the manufacturer's specifications, it recommended that I use clamping diodes externally to reduce transient voltage spikes effects on the system. So they're connected to each output of the circuit, and this was also necessary because the DC motors would be turning on and off, causing transient voltage spikes. And then I have the two decoupling capacitors, one for the logic supply voltage and the other for the motor output supply. Here's the finished PCB right here. So as we mentioned before, there's terminal block J1 for the switch, or sorry, J1 for the power, J2 is for the motor outputs, J3 for the LDR inputs. There's a switch connection here. There's my 2 amp fuse. This is the L293D or NE motor driver, and this is the LM33N comparator. Here's RV1 and RV2 for the x-axis window comparison configuration adjustment, and here is RV3 and RV4 for the y-axis adjustments. So we'll get into the first test that I did. It was the baseline panel comparison test. This setup was exactly the same as my main data collection phase. So I just essentially did not use the tracking method involved with my first system. So I set the panels both up at the same angle, facing the same direction for the same amount of time. And the goal here was to see if there was any baseline discrepancies between the panels. I figured since they were both from reputable manufacturers that there wouldn't be much more than a couple percent of a difference. So here's the results from that. As you can see in here, I had about a 1.2% more power output from the PV panel 2, which is the fixed angle panel. I consider this value to be not that significant because I was expecting about 20, maybe 30% increase in power overall from the tracking system. So the second test I did was a sun sensor sensitivity test. So this is just here as a reminder for the configuration of the LDR sensor. This test was rather hard to do accurately. What I did was I had the panel set up facing a light source, and I made that the panel perpendicular to the light source. Then I would take that light source and move it in a directional axis until the sensor would send a signal and make the motors to move. When that would happen, I would stop moving the light. I would measure from the point of origin the distance that traveled, and then I would repeat this. Then I would reset the test to bring the light back to the point of origin and set the panel up back to perpendicular with the light source, and I would repeat this about 10 times per axis. So doing so, I was able to do 3 of the 4 axes. I was not able to do the down axis, so bring a light source down below the ground. I tried to set up in the lab to try to get to work, and I'm just not getting good readings to be able to get a good, accurate measurement. My data here showed that had about a 20-degree, the light source had to be about 20 to 26 degrees, depending on the axis here, for it to enact a change in the sensor. These values were rather hard to obtain, and I would like to actually do this test again with more time and more accurate equipment, because I really feel like I can nail down how accurate this sensor is. So next we'll get into the data collection phase. So when I was recording data, I was recording data at a very high sample rate of about 25 hertz. So this gave me tens of thousands of data points for the day. So to show this data, I decided to bring it down to 15-minute intervals, so it was more presentable. So we'll start off here. I have the 15-minute intervals here, the timestamps. Here is panel 1 dump load voltage, panel 2 dump load voltage, panel 1 shunt voltage, panel 2 shunt voltage, the interpreted current for each panel, and then the power output for each panel at each time here. Then I was able to find the average of each. I found the sample average and the population average just to make sure that the sample I chose wasn't too small, to ensure that it was an adequate size. So the results from this first day of testing was about 6% more energy output by the tracking panel. I thought this was a very low value. It being the first day of setup, I kept checking the system. I might have, been around it too much to maybe enact a change. So I considered maybe just the first day. This is why I was seeing such a low value. So this is the data for the sample data for that day. As you can see, the tracking panel here in blue is consistently outperforming the fixed angle system till about 3:30 here, where then they both drop off. At this point in the day, on my observations, I made that there was good cloud cover that rolled in around 3:30, and that's why we had such low readings towards the end of the day. Next, we'll get into the second day of data collection here, May 16th. This was an unexpected day of data collection. It was very cloudy this day, rain periods and such. And I had actually found that the fixed angle panel put out 10% more power than the tracking system. This was really not expected. I was in class most of the day that day, so my observations did say that the tracking system was struggling at lunch when the cloud cover was too thick, where I would left for lunch and then came back and it was still facing the same direction. Here's the visual data for that day. The discrepancy here is from me setting up in the morning, right at 8:30. As you saw in the shading analysis, the sun was coming around the side of the building, and I thought the angle in which the panels were sitting, that I needed to move the fixed angle panel ahead so that the tracking panel wouldn't block it for the first 10-15 minutes of data collection. Doing so, the light hit the fixed angle panel first, so that's why it started off ahead of the tracking system. Then it was sunny until about 10:30 here, and then it got cloudy and terrible for the rest of the day, where the fixed angle panel outperformed the tracking panel for the duration of the rest of the day. Again, I think this is mostly due to the sensor not working well in low lighting conditions. I think the sensitivity of the sensor needs to be adjusted for different weather conditions. And then the last day of testing here was a sunny day all day. However, I only did see a 1% increase in power, which I was not expecting. And again, I'm expecting much more than this. This is the data collection here. It was sunny and had a nice flat trajectory here until about noon, and then it got cloudy for the rest of the day and actually started raining. Again, it's kind of all over the place here. The fixed angle panel performs till about 1:30, and then they're about the same, and then the tracking panel takes over for the rest of the day. On to the last day of data collection. This is probably the best day of data collection that I had, where it was sunny all day. One factor that could have played an impact, it was very windy that day. I was only planning on running the system up to about 30 kilometers per hour average wind. However, this day there was 65 kilometer an hour gusts. So being the last day of data collection that I had to do, I decided just to push through it. However, I don't know how much this affected the data. I only had about a 2% increase in power. Again, I was not impressed with this and had me scratching my head as to why I'm getting such low values. But if you look at the tabulated data, the tracking panel seems to be doing its job here, where at the start of the day, the tracking panel has a nice flat trajectory, whereas the fixed angle panel slowly rises, and then it continues a flat trajectory until the end of the day, here where it continues flat and the other one starts to drop off. Now this is closer to what I was expecting to see. I was expecting to see more of a flat trajectory from the tracking panel and the fixed angle panel to have more of a bell curve. Here's the summarized data from the 4 days of data collection that I was able to do. As you can see, the first day was the biggest improvement by the tracking system of all the days. This day was a deficit, and I'm thinking it's due to weather there. So that brings me to my question that I asked at the start of this. Is dual tracking worth it? Data analysis that I conducted is not conclusive to support the theory that I set out to prove. The data shows very little increase in power production, and it was expected to be at least 20%. The cost of the tracking model, minus the solar panels and the data collection equipment, was about $480. And then the fixed system was about $10 of wood and screws. So then I was able to find here that it was much, for the data that I collected, it's easier to just add more panels and more cost efficient to increase the power output. So in conclusion, I found that the tracking system is not worth the extra cost and complexities over a fixed angle system, but that still had me wondering why I came to that conclusion. So I have a theory for this. So here we can see the sun path chart for Moncton. This chart is in standard time, so I have the data collection here from 7:30 till 3:30. So I'm collecting for 8 hours of the day, but in reality, I'm missing almost 6 hours of data collection time here. So this is the time where the sun would be at the lowest angle from the most east and the most west points in the sky. And this is where I think that I'm missing my data. And to support this, if you look at some of my graph data here, near the start and end of the day, it's consistently a wider variation between this tracking panel and the fixed panel. And this occurs for most of the days here, especially. You can see at the start and end of the day, even on the cloudy day. And then, as I mentioned here earlier, we have the nice flat trajectory from the tracking panel, and then the fixed angle panel dips off at the start and end of the day. So future testing considerations. So two improvements for sure that I would make on the system is to make the testing window larger. Leaving the system out 24/7 to track and utilize that low angle light, I think would give me the data and the expected results that I was looking for. I think the more data collection days, ideally collecting data for an annual comparison, would yield more conclusive results towards supporting a tracking system. And I think the other factor might be is my sensor isn't sensitive enough or might need a better calibration setup. I think even purchasing a more accurate commercially available sensor might improve the data collection as well. So thank you for your time. Next I'll be doing a visual demonstration of the system working here. So I'll just turn the system on here. Let's adjust to the ambient lighting in here. And then I'm going to use this light source here. It's much more reactive on the y-axis. Something happened on the last day of data collection with the wind, where the x-axis is much more laggy, it feels like. Perfect. And that concludes the demonstration.
Anybody wants Sorry?
Just a question about the, what is the fixed angle that you use?
I use 45 degrees. So I just chose this as, it's halfway right between vertical and horizontal, and it's also for Moncton close to the fixed angle position for optimal.
And during the month of May, what do you expect for an optimal angle? I would want to go with fixed.
Just for specifically the month of May,
Yeah.
it would be the latitude minus 15 degrees, I believe. So it would be closer to about 31 degrees.
You sure?
Off the
Oh,
top
yeah,
of my head.
sorry,
Yeah.
yeah.
So one thing, like, I was thinking, like, why you didn't get the results you were expecting is you only collected for, I think, for May, right?
Mhm.
Yeah. So that could be a reason for you. That's probably why.
Yeah, but I would have seen an increase in power output by the fixed panel consistently if it had the optimal tilt angle
It's
for
not
the location.
It's not just that. It's during the year, the what do you call that? The track system would be able to track more. So
I think that what happens in May, the spring and the fall is 45 is probably
Yeah.
pretty close to the optimal angle anyways, because it's a compromise, right?
Yeah.
45 is the difference between the 30 and the 60, right? So in the winter you're at 60, in the summer you're at 30, and in this case you're on a shoulder season, so it's the middle. So you're not seeing the benefits of, for example, in the summer where you should be at 30, but your fixed panel would still remain at 45. Right? And in the winter it would have been the other way around. It should have been at 60, but your fixed panel is still at 45, so you would have seen the benefits. However, I was really interested in the fact that you looked at the shoulder times, and yeah, you're right, there's 6 hours there that maybe don't produce a lot of energy, but they do. That's what your tracker is all about, is gathering as much of that energy as you can. And yeah, it'd be interesting to see, had you moved away from the building, or not had the building as a block. So I think, yeah, your setup was handicapping you in the fact that you were not measuring at the times where this excels, right? You were more measuring at the time, and not only the time of day, but the time of year where the fixed panel is at its best. So
Yeah.
you mentioned that there were days where the sensor wasn't tracking well, like overcast, or and you said, well, maybe if I had a better sensor. I don't know if a better sensor would change anything, but there are other solutions to that. Can you think of a few more solutions that would help you out?
Yeah, an astronomical tracker. So this is where it would track the sun's position basically across that sun path chart. You have a predestined positions that it's going to go to through the day, and you can have it track those positions too, so you can see how much amount of variation there is due to other impacts as well. So.
You could even have a combination where you do the astronomical for certain periods, and then you use your tracker to fill in the blanks, right? Type of deal. So that would have been interesting. Yeah, that's good.
Did you measure the power consumption of your tracker?
It's 6 volts at 0.04. If it's like less than 2 watts, I believe. Yeah.
But that can't be consistent all the time.
No, but that's just that's without motor consumption. But just the tracker itself, I know, wired up with the LDRs and such, it draws 0.04 amps. And
that would be interesting. The cost is not just a cost financially; it's the cost power-wise. What's it costing you to keep that thing going?
That was kind of the original plan to do, but then I realized it was quadrupling my cost due to having like charge controllers, batteries involved. Because the idea with that was I could have leave it out just in the middle of the field somewhere with the batteries going and then just do a power consumption. But to simplify it to just the output due to tracking, I decided to do that as well. Because that's where I get into, if I charge the battery up all day, I gotta drain it off. and things like that.
Yeah, I don't see where you would have needed that though. Like, the reality is all those would have been the same for both systems, so you could subtract that, right?
True.
And really just look at how much is this thing drawing surplus, right? So yeah, so no, it would have been interesting to track that. Could you go? Alright, schematic, I guess.
So, I guess why you want me to zoom in on there, so I didn't have the full thing.
So for your motor control, there obviously a bit of elaboration. I noticed you had two. You have two capacitors down there.
Yes.
What's their purpose?
They are decoupling capacitors, so they decouple the IC from transit voltages of the circuit.
Okay. So, again, typically in a schematic, we're a little less worried about the physical location of things, but it is kind of traditional to things like capacitors, place them near to their actual location than they should be. So is that a good location for where they should be in your case?
On the schematic, probably not. In reality, with my PCB, I put them as close as possible to the supplies.
The supplies to?
The VCC1 and VCC2, right here.
Okay. Going to where though?
So these are connected across from the voltage supply to the ground.
Okay. And on the ground side, where did you have consideration to where you're attaching on the ground side?
I use the ground plane, I believe, on the PCB.
Because that's another thing that people forget. They try to show those capacitors as close to VCC1, VCC2 as they can. The reality is they're supposed to go across there to your ground pins on the other side. The closer they are there,
Yes.
the more effective they are, right? It's sometimes hard to do with just one or two layers there, like 3 layers, or 4-layer boards work out better that way, but nonetheless, it is, for those to be effective at what they do, is they have to be really across VCC1 to ground pin 4 or 5, I guess, and VCC2 and ground pin 12 and 13. Otherwise, they're not as effective. Right?
Yeah, okay.
Don't forget the power coming into the system via +6 volts has to go out, the power of the current, it has to go out via the ground, right? So if the same condition exists on the ground side, it's like pushing on the road, right?
Yeah, that makes sense.
So you have RV4 there, and I think there's another one a little higher there, RV3.
Yes.
And those do what again?
These can either move up or down the window comparator, so the VREF high and the VREF low. So I can either widen this window, I can narrow it, or I can move it up or down, depending on where it wants to sit.
Did you find their tuning, for a better word, was difficult, or?
I did find it difficult. Mainly when I was trying to balance these, it's, pulling on one end or open or other, right? Most section parts here. So I really tried to get them to as close to the values I was intending them to be. I did have the 2 volts window for this, all my testing and such, but I did play around during my early panel comparison test back in March with the sensor at 1 volt, and it seemed far too sensitive and almost would hunt, as you'd say. So that's why I left it at the 2 volts there for that.
So, yeah, as you get closer to your optimum values, then you encounter stability issues, right?
Yeah.
So what's one way of ridding ourselves of those issues?
Stability issues. I'd say a better calibration process to sensitivity.
I think you'd always encounter what would happen is you'd get it right there, oh, it's great, next day it'd be doing it.
Yeah.
So what would be another way of dealing with, for example, hunting?
I'm not too sure.
Well, why does it hunt?
It seems to be in the low light conditions where there's like other shading coming into play. Because the other thing about the sensor too is it wasn't against a vertical plane, it was against a corner. So it had like weird shading interactions with that. Again, that's another thing I would have liked to design around if I had more time to spend more time on the sensor.
But system-wise, why does it hunt?
Those LDRs are varying voltages that has the V in going and hitting the VRF below too fast.
Yeah. So the way to rid yourself of that was to do what? Make the window wider. Then that makes it less sensitive.
Yes.
Right? So as you get closer to the ideal of only having a value, not a window, it will encounter, and that's going to happen no matter what. So what do you think causes that? Think of the electromechanical aspect of your project.
It could be the accuracy in which the motors move or react to.
Sure.
Like if they turn on, they'll move it X amount of degrees, but if they only need to move, it moves more or less.
So why does it move more? Typically it's more than less. What does your array have, physics-wise? It gets worse if the panel gets bigger and bigger.
Oh yes, torque.
Not torque.
No.
No. Doesn't have. If you have a big boulder, you want to move that boulder, and as you get a lot of torque to move it, does it start moving right away?
No. So it has
You have to overcome static friction,
Static
and when you
friction,
get it going,
friction.
and you want to stop, does it stop right away?
Yeah. Okay, that makes
Does it?
sense.
No, it keeps going, right? So it has what?
Momentum.
Momentum. So this has momentum, right?
Yeah.
So your little attempt at moving, well, the motor has to give a little bit more to, and it goes over. Oh, so it goes back. And that's what having that window, what's that window called? What's the technical word for that? Putting a window like that.
Sorry, to do with the momentum where
Oh,
overcoming
the
friction?
your window that if you make it wide enough, it doesn't hunt.
Oh, the window comparator?
No, there's a word for it. It starts with an H.
H.
Ends with an S.
Sorry, come on.
Hysteresis.
Oh, hysteresis, yes.
Okay, so we put hysteresis in it, but hysteresis still, as that window gets smaller, because hysteresis is just a way of making it duller, right? Like less sensitive. So, right. Yeah, that's right. Right, we're just trying to prevent the hunt by making this window where it's not sensitive, right? You know, but as you're closing it, and again, because of momentum, it's going to be more difficult. So what kind of system, we talked about this in the lab one day, that's why.
Yeah, using a system that can, a driver that can slow start the motor and then slow stop the motor. So you're not having a full start and full stop. So as it's slowly moving and slowing up speed, right, and then getting to the point, you slowly stop it down so you don't have that transfer momentum.
So I'm not asking you necessarily what the system is called, but what does it need for that to happen? There's an essential part it needs. It needs to know something.
Oh, it needs to know the relative movement caused by each motor interaction.
Sure. It needs to know where it's at,
Yeah,
right?
point of order.
So it needs what?
Needs to know the radial angle in which it sits, right?
So there's a measurement that the output that we need to give back to the input. What's that called? Taking the output of a system, bringing it back to the input.
Feedback.
We need to have feedback. So we need to have things like PID, things like that, proportional, integrated. So we need to know where we were, where we're going, and how fast are we getting there, right? If we have those three things, then we don't have to worry about hysteresis or things like that, because now we'll know exactly where we are and how close we're getting to where we want to be. So that window disappears, right?
Yeah, makes sense.
Anybody else? That's a whole other project in itself.
Thank you.
For me, still, it's like a radar. Between that and the sonar, put a gun on it. It's done.
How's my hair? This is one of my brother's paintings since he's been a kid. One of my his brother was his friend. So no, but their father just passed away. His father had cancer. And a year ago.
It's also cool. You can see I have my tech
His road is kind of high.
I have to check this, the mark has like a shipping deal.
Thank you.
Yeah, I saw that here. Is that what this box is for?
Brian told me that his project is not.
I was trying, I was simply,
It's like, that's goddamn.
Friday was not.
You didn't say labor chart? Oh yeah, it's big. Yeah, man, this is why this is my other pocket Insulting me. No. Oh yeah, they got like 2 kills this bitch. Gen Z.
Okay, everyone, so we're Now, there was a slight change in the schedule this afternoon, so instead of having 2 more presentations, we only have 1 now. So I present to you Amrapali Chauhan, who will present her solar-powered light for a bicycle.
Thank you, Mr. Good afternoon, everyone present here. I welcome all my instructors, my classmates, electronic class, and the online audience. Thank you for everyone to be present here. Okay. My name is Amrapali Bhagwan Singh Chauhan, a student of Electrical Engineering Technology Program, Alternate Energy System Pathway. I came here with the vision that I want to study renewable energy and sustainability. And that's the reason why I enrolled myself in this course. My project advisor is Mr. Jua, and I thank you for your support and guidance throughout my project. So let me quickly walk you through all the contents that I have for my presentation today. First, we'll start with the introduction, where I'll be talking about the background, the purpose of my project, and why this project is so important. Followed by the proposed design, where I'll be talking about the concept diagram, the block diagram, the schematic diagram, as well as the PCB design. Followed by some tests that I conducted. We'll be discussing about those and their results. Next is the actual design. Here I have clicked some of the actual finished project photographs that I would like to show you all. And last but not the least, the summarizing of whatever I have done so far, conclusion and the future scope. Let me brief you about the background. Back in home country, my father is a farmer. I can remember, not vividly, but when I was a child, I used to go to the school on cycle. When it was dark during the winter, like 5 a.m., 6 a.m. in the morning, it was difficult to ride the cycle. My dad used to come with me with a torch or something that would help me navigate to the school. My school was in a village. I come from a background where it was far located from my home. The same problem I faced here when I landed here in Canada. I wanted to explore some of the places around here, so I bought a cycle. And during the summer, if you see these pictures of mine, this is from the Mapleton Park here, where you can see around it's quite sunny, surrounded by the big trees. While returning to home, it was dark, and I faced difficulty while returning home. And I was always curious to ask myself why the manufacturers of the bicycles don't equip lights as a standard feature. I don't know if you have the same question. So that brings me to my purpose, why this project was important. I wanted to propose a design which can use the solar energy and can store that energy in the form of chemical energy and can be used to light a LED light for the rider. That's converting again into the chemical energy to the electrical energy. Talking about the importance of my project, I would like you to view this statistics that I have here to show you. It's the distribution of the bicyclist accidents by the time of the day. It's 2021. The source where I got this information is given below at the bottom. As you briefly analyze this, the first is the time during the day. the number of accidents occurred, and the last is the percentage. As you closely see, the number of accidents occurring during the time from 6 to 12 is maximum. And that too, if I talk about 6 p.m. to 9 p.m., it's the highest. This brings the importance of why the lights are actually necessary for a bicyclist to ride in the dark. This was the important point for my project consideration. So these were some questions I asked myself. Why do many bicycles not come equipped with lights as a standard feature? I have seen bicycles, e-bikes in Walmart as well as Costco, ranging from $2,000. Still, they don't have lights. Why? What role do lights play in enhancing cyclist safety and reducing potential risk? Why are lights considered essential for ensuring the safety of cyclists on the road? Again, the source of that picture is given at the bottom. For any copyright issue, I have given all the sources at the bottom. So, combining all this, the proposed project, the importance of solar light, I proposed a design for my project where I'll be taking you through the concept diagram, block diagram, schematic, and mechanical diagram in detail. So what is a concept diagram? Concept diagram is basically a visual representation of the concept or the ideas that I had in my mind while coming up with this project. So as you see, this is the top view of my product. On the top, I have the solar panel where you can see two LEDs, one which is the full and the other is indicating charging. This is the front view of my product. You can see there is a light, LED light at the center, and around it on top I have placed a lens. This is the side view of the product. You can see there is a switch at the bottom. I have used the switch as a rocker switch for turning on and off the light. All the indications are here at the bottom, as you can see. Let's talk about the block diagram. What is a block diagram? So block diagram is basically a representation of your project in terms of blocks where you connect all the blocks with the flow, signal flow indicating where it goes. So the first block is the sunlight coming to the solar panel. From there, the signal flows to the battery charger circuit, where it is actually comprising of a voltage divider, a transistor, a relay circuit. From there, the signal is going to the batteries, where the batteries are being charged. Here I have used the battery as NIMH, AA, each rating of 1.2 volts. From where the signal flows through the DC switch regulator IC, I have used this as a 7805 IC. As you see on the top, the user on and off LED switch is indicated by a broken block, which actually indicates that the signal will only flow once the user will give the input. So as a user is giving the input, the signal flows, and you get to see the current flowing through the LED and closes the circuit, giving the light output. This is the basic representation of all my components, a schematic diagram. I have divided the entire schematic diagram into 3 different parts, in which I will be discussing more in detail in further few slides. As you can see, the first part is comprising of a voltage divider circuit, and a transistor with a diode. The second half of the circuit is having a 5-volt relay with 2 LEDs and a current limiting resistor R3. At the end, I have the battery connected to the terminal block J2, and I have a regulator IC U1 connected to the LED in series with a switch SW. In order to operate this product, if there is any fault, I have labeled SW as user on and off LED switch. So in case in future, if there is any problem, they can see the schematic diagram and they can turn or adjust whatever they want to do. Similarly, you can see at the potentiometer, it is indicated as battery cutoff voltage setting, which I have used to set the voltage for my battery to be cut off once it is fully charged. So again, any user can see this and read it and set it according to its battery cutoff voltage. So let's try to understand the schematic diagram in detail. Junction J1 terminal is the solar panel connection. I'm using a solar panel of 5.5 volt. It is a polycrystalline material and it is having 60 milliamperes capacity. If you go further, there is a voltage divider circuit R1 10K and a potentiometer 10K. Assuming that the current is flowing through this voltage divider circuit, I can calculate the current flowing through this voltage divider. So if my voltage at the panel is 12 volts and the total resistance, if I calculate for current, is 20K, I am getting a current as 12 divided by 20, that is 60. And the minimum, if I take, it's 12 divided by 10. Can I use? So I'm getting 12 volt and R1 is 10K and R2, that is my potentiometer, that is also 10K. So the total resistance will be 20K. My voltage is 12, so I can calculate the I as amperes. That's the maximum current I'm getting. Next, followed by the transistor current. I've selected the value of R2 as 1K based on the base current that I want the Q1 to turn on. As the signal is flowing from the relay, as you can see here, through the common terminal of the relay 2, which is connected to the pin 4. Further, it is connected to the battery. So when you go out in the sun, the battery is getting charged through this path, from the panel to the relay, through the diode and to the battery. So in this way, my battery is charging. At the same time, the green LED will be turning on, indicating that the battery is charging. Next, assuming, let's say, the battery is fully charged, where you have set the cutoff voltage. For example, my battery is 3.7 volt batteries and the cutoff I have set is 4.2 volts. So it will automatically cut off the battery, will isolate the circuit, and the red LED will turn on, indicating that the battery is fully charged. So as you can see, the Q1 is on The common terminal of the relay is connected to the red LED through the current limiting diode. And the signal is flowing like this. Let's assume that the battery is fully charged, and once the user is turning on the switch, as you can see here, SW is closed. The current flows through the regulator IC, where C2 and C3 are the input capacitor and output capacitor, where C1 is used to filter out any ripples coming through the battery, whereas C3 is used for any transient response, giving 5 volt as an output to the LED. Here for my project, the LED I am using is 3 watt LED. So as the circuit is closed, the current flows through the switch, through the regulator IC, through the LED with the battery completing the circuit. This is the mechanical diagram of my project. Throughout this project, it's been a learning journey. When I was trying to do my PCB design and I shouldered all the components, and when I was doing the testing, I was not able to charge the battery because of the voltage and the current. So I decided to use 2 panels instead of 1 panel. So I connected 2 solar panels in series, giving me around 12 volts and a current of 60 milliamperes. So for that case, I have to drill 2 holes for 2 panels on the top. These are the 2 holes for the LEDs. The front is the bigger hole for the lens. And on the side view, you can see there is a hole for the switch, a rocker switch for the user. This is my PCB design. I faced some challenge while designing this PCB for my project. The track width here I've considered is 40 mils. As you can see here, I have included a logo. Trying to add a logo using the image converter, I somehow deleted all the saved files and I have to redo it again. I was way ahead of my PCB design, but trying to do something new, learning to add the image actually cost me the time. I was behind submitting my PCB design. But Mr. Ledger also helped me with the drill holes that I have for my project by looking close to the enclosure that I have purchased. The top one is the front copper and the bottom one is the back copper. So there were 2 tests that were proposed for this project. The first one was the battery charging time measurement, and the second one was the lux level measurement. So this was the setup for my battery charging time measurement, but unfortunately due to weather conditions, I was not able to complete this test. But as you can see, I have given a source and I have roughly estimated that if the battery capacity is 2600 milliampere hours and the device consumption is 300 milliamps, my total time estimated to charge my battery is going to be 8.667 hours. As you can see, I tried to do the setup for my testing. This is the back side of the E building at this campus. It was extremely cold and windy, and I have to go back and fro, and it was really cold, and even you can see I have been wearing gloves. The second test was successfully conducted. It is to measure the light intensity. So here the picture you can see here is of my basement where I conducted this test. For conducting this test, I placed the light at a certain distance, considering that I can't bring the cycle inside the basement. So I created a small height where I kept the light, and I measured the total distance. If you see here, the total distance was 7 feet. And on the front there is a wall where you can see the light is illuminating, and you can see there is a curve where actually you can see how much the light will be illuminating actually on the rightest path. The test was conducted with this device which I borrowed from the lab. This is known as light meter or lux meter, where it has a sensor. Placing that sensor near to the light, you can actually calculate the total lux. So at different feet, right from 1 to 7, I calculated the number of the light intensity in lux. Based on this, I got the graph like this. As you can see, this is the lux that I have calculated. The maximum 744 is indicating where the light was placed, when the light was placed exactly close to the sensor. And moving further, 1 feet, 2 feet, extremely at 7 feet, I got a very less amount of intensity that was around 21. Here I would like to make a correction here. As you can see, that's LM square. So that's just LM lumens. And based on these values, I'm getting a graph which is actually self-explanatory, that as you go further from the light, the intensity decreases, or vice versa. After conducting this, I wanted to have a reference whether my test was actually good when I go out in the field. So I use these two references, and both the reference sources are given at the bottom. So as my maximum lumens was having around 700, I can say that I actually fall under the rule where I need 200 to 800 lumens. So I successfully conducted, and I was actually happy that it actually gave me some amount of lux intensity. Second reference I am taking for is the 3-watt LED that I have. If you compare that 3-watt LED to a CFL 6-watt and others, it's 250 lumens. But I am getting 700. That was really interesting to know, and I was happy about that. At the end, as you can see, this is the picture of the finished product, where you can see the 2 LEDs, the lens, the switch. This is a hook or a handle belt that is securing the light on my bicycle. This is the front stock view, where you can see I have used 2 panels, which was actually necessary for my testing. These are some pictures of the night. Here, as you can see, as I was taking the picture, there was a reflection of that reflector. But in the second picture, you can clearly see how it is illuminating the rider's path. So the entire project I've divided into 4 quarters, where actually starts from November till May 19, where I was recommended to change the IC that I actually proposed in my formal report. If I have used that battery IC, my product would be more compact, less in weight, and more efficient. Other challenges I faced during this was the grounding for my PCB design. I was not able to do the grounding for the back copper for my project, and I was really struggling through, and one of my classmates helped me with that, and I was really happy to do it at the end. Coming to the conclusion, I would like to summarize that I was able to successfully make a light which is actually powered by solar and ready to use. The only challenge I faced was that I was not able to do the charging test, but given the time and the weather conditions, I would again like to do the test to see how much time it takes compared to the reference value. I also tried to change the battery capacity from 2,300 milliampere hours. I tried to buy a less milliampere hours, but unfortunately I was not able to do the test as well. So summarizing, I would like you to all take away two main important key points from my project. That this project is using the power of sun. In that case, you are actually reducing the carbon footprint. And the second important thing is the safety. By implementing this light, you are actually not only safe to ride the bicycle in the right, but you are also providing visibility for the person coming from the front. For example, the turns and other far distances. Next is it was energy efficient because there was no use of electricity. Here there is a typo in my electricity. Second, it was cost saving as I have used rechargeable batteries, so I'm not dumping the primary batteries into the waste. And the last one is accessibility and convenience. So this product is very easy to install using the belt, and it is low maintenance. In the future, I would like to conduct few tests where I would like to implement some of the SMD components which will be having lightweight, more compact, smaller enclosure. It can also inbuild some of the features like a buzzer, sound, camera, Bluetooth, sensors. When I was designing this project, I kept the weather conditions in mind, not only from Canada, but also from my home country, where there is extreme hot weather. So I wanted my product to be water resistant as well as heat resistance. So some tests can be conducted in future for the enclosure. My product has the battery inside it, so if you want to replace it, you have to actually open the entire case. So in future, I can choose a different enclosure with a separate battery case. With advancement in solar panels, if I find a more powerful output panel, instead of using two, I could have used only one panel. The overall cost of my project was $52, which was actually less. When I proposed it, it was around $300 to $350. The reason is I designed this, I proposed this amount keeping in mind that it was to be designed outside. That is the only reason. The only costly part for my project is the batteries. They cost $20. At the end, I would also like you to thank all my friends, my instructors, my advisor who helped me, supporting me throughout my project, Mr. Ledger guiding me for the PCB design, Mr. Metcalf helping me with the LED, the grommet, Mr. Kadahi for my communication skills, Mr. Salal for my upcoming projects, and this is it. Thank you for listening to me. So now I'll be demonstrating my project. So this is the front view. Sorry, this is the top view of my product, where you can see two LEDs. I've used a grommet for securing the LED. I faced some problem with the LED. When I was trying to do the testing, I actually short them, and instead of red LED, I have to use the both green LEDs just to indicate that it is charging and fully charged as proposed in my schematic. In order to solve that problem, I used the heat sink that was actually separating two terminals of my LED. On the side, you can see there is a rocker switch, where you can see I have indicated it is for the user on and off switch. The front of the product is having a lens which is actually placed on the top. I have actually drilled holes and then I have inserted this, and the lens is actually placed on the top. At the back, you can see there is a secure belt, and also I have mentioned important note that it is only recommended to use the rechargeable batteries for this product. So let's try to place this on my bicycle. So this is the lux meter that I have been using to measure the intensity of the light. As I go closer to this, it is showing me out of this, so I have to increase the, maybe this is because of the other lights also impacting the reading. But whatever the number is, I have to multiply that by 10. So right now I'm getting 7,700. As I go closer, it's increasing. So the distance here I've measured is 7 feet here. And you can see it's 2. So 2 multiplied by 10 is almost like 20 lux at a distance of 7 feet. That was very actually close to what I had in the basement. So So that is the end of my demonstration. Thank you.
Anybody first?
And I welcome any questions or suggestions for my project.
Could you bring up the slide for the accidents versus time of day?
Yeah.
Could you turn off your project?
Sorry, sir.
Thanks.
When I was testing, it was always in my eyes.
I'm seeing dots.
This one?
Sure. So, my question, I guess, is, that slide shows, obviously accidents happening after whatever time it was there. Yeah, there, after, let's say after 3 p.m., right? It becomes significant. But I don't see in that slide where it says that the accident is due to low lighting.
So it doesn't say that it is due to only lighting, but I think one of the consideration that majority of the accidents are occurring during the night is the light.
Well, that's fine, you think, okay? You have to be careful, okay? For me, it was, you're putting a slide that supports your thought process, but it doesn't necessarily clearly,
It says,
causation doesn't necessarily mean.
yes, I
right?
do get your point, but in the source, if you go through, it do says that it is one of the cause,
Okay.
not the only cause,
Yeah.
but it is.
But again, I would ask how much of it is it, like, I'm not, I'm just
Yeah.
trying to say.
I only
when
have
you
this
show
data,
some
it
of
has
this-
not separated or bifurcated, like only the accidents are due to the light case. It says during the time of the day.
Okay. Because again, for me, for example, between 3 and 6, I don't see that as being a very common time to have an accident because you're not seeing where you're going, okay? Whereas, okay, after 6, we can start saying perhaps, but then again, does that 22% and that 17%, how much of that percent is due to that, right? If it's 1%, I'm pulling up numbers like you are. If it's 1%, it doesn't really support your cause, right? You know what I'm saying?
Yeah.
So you have to be careful of that, right?
At those times too, it is typically rush hour, so there's a lot more
Yeah,
traffic.
exactly,
So
that's what I
that
was
would
thinking.
imply more accidents too, right?
That's what I was.
In winter time, it could be darker earlier, that's another
Sure.
consideration.
Yeah.
But it doesn't say geographically where they're.
Where the accident happened.
Right.
Yeah.
That's a lot of.
Yeah, exactly. I mean, it's a very nice graph, and looking at it quickly, oh yeah, but at the same time, you have to be careful because if you go digging at the numbers, it might not, and that's, that happens a lot. We they always say, oh, statistics, they can prove anything. Well, this is what they mean by that, right? You've got numbers there, but they don't necessarily directly support what you're. All right. Could you bring up your schematic? K1, yeah, that's fine, K1. K1 is G5Q1. When I was looking at this schematic at the start here like this, and Mr. Broad actually mentioned the same thing here, so I'm kind of speaking for the both of us. I was really confused because I did not understand how when that coil, my assumption being that maybe that coil right now is, again, normally open, whatever. If that coil went to the opposite state of whatever it is, how LED 1 would ever light up. Okay, because you you have the symbol wrong. If you go look on the data sheet, pin 2 is the throw for the armature. Pin 3 and pin 4 are the two outputs to the relay. All right. But in this case here, that's not how you've laid it out. You've laid it out as pin 4 being the throw, and pin 2 and 3 being the outputs. Now you correct it during your explanation, because if you hit the button a few times, it'll show the when you activate the coil there. Eventually, no, one more thing there, and you're swinging pin 2 down to pin 3. But again, that's really not how that symbol is laid out to be represented. Okay, so I would say actually you're kind of lucky you didn't get an error in your PCB if this was the schematic capture you use. Okay, so again, in this case, the armature should be on pin 2. Okay, and 3 and 4 are your outputs, but on the symbol, that's not how it's laid out to be. Okay. I don't know if I'm the only one that brought it up, because Mr. Brown indicated that too.
The relay that I had has the common terminal as 2 indicated,
Yes.
and 3 and 4 are the
Yes, I agree. Now, the symbol for this relay is go to a previous one. Okay. On this one, what's the common pin according to your drawing? It's not pin 2. It's pin 4.
It's pin 2.
No, it's not. No, it's not. That's not how that swings.
If you see here,
I understand in real life it is.
Yeah.
Your drawing is drawn wrong. Your drawing is incorrect.
The symbol.
Okay?
You should put 2 on the top,
top.
and 4 and 3
Yeah.
on
At
the
the
bottom.
And like I said, if you use this for your schematic capture, you were lucky that it didn't cause an error. Because again, yeah, it should have been. Okay, go compare it to the data sheet.
this
That looks better.
That looks better, yeah, exactly.
I used for the explanation. I modified the footprint to show the current flow through both the LEDs.
Well, again, the way it's laid out there is not identical to the way you have it in the
Yeah,
previous.
yeah. I think I changed the terminals 2 and 4.
That looks better, but it should be nearer too, because if it goes in position 3, it's not gonna work.
No. There's actually a wire missing there, I think, compared to the other one. Anyway, you need to look at those two and straighten that out there. That's not fair. Your regulator, U1, 7805. Mr. Brad wants to know why you don't have a diode going across pin 1 to 3.
Pin 1 and 3.
Yeah, we've seen that in the previous examples for other regulators.
Yeah.
So why don't you have a diode across pin 3 to pin 1?
Considering that the current flowing through the LED is around 300 milliamperes.
But that's not what that purpose. That's not the purpose of that.
No, like when there is a current flowing, I calculated it was 300. So in case when there is current more than that, I need to have a diode which can protect the U1. Is that what you're asking?
It's got nothing to do with the current. U1 is sensitive to the fact that if you have the condition where pin 3 to ground is higher voltage than pin 1 to ground by a couple of volts, it will push current back into 7805, especially when you have capacitors there, okay? And for example, if you short pin 1 to ground by mistake, or something shorts out your battery or whatever, okay? Then what happens is your input pin 1 becomes lower voltage than pin 3. That will blow your 7805. If you go look at the spec sheet again, the manufacturer clearly indicates you should have that diode there. My question though is, a 7805, you're trying to be very efficient here. A 7805 is a series regulator. What other type of regulator would have probably been a better choice?
Different regulators?
Yeah. Different type of regulator.
Like this is a positive voltage regulator? Like 5
No,
volt?
this is a series voltage regulator. How does it regulate the voltage? How does, let's say on the input side there's 10 volts. I'm going to be extreme here. There's 10 volts. And on the output side you require 5 volts. Where's the difference in, what does it do with the difference in voltage? Where's the difference in voltage on? It's going to be
With
across pin 1 and 3, right?
1 and 3, yeah.
So you're going to have 5 volts across there, okay? And I know you're going to draw, let's make numbers easy, 1 amp. So 5 volts, 1 amp. That's how much power?
5.
5 watts.
watt.
Where's that 5 watts going?
It's dissipating
As?
as heat.
So not very effective, right? Okay. What's another type of regulator we can use here that won't suffer from that?
We can use the heat sink.
Well, a heat sink's just going to get rid of the heat. It's still the same problem, right? You're not being very efficient with your battery, right? I would say look at a step mode regulator, a switch mode.
Like
switch
putting
mode.
a resistor and adjusting the
No, a switch mode regulator, something that uses
SNPS.
switching, whatever you want. Okay.
What is your battery capacity here? You said you had multiple batteries.
Yes. So,
What's the total voltage of your batteries?
yeah. So I used NMIH 1.2 volts each, a total of 4, that is 4.8 volts. But to get output 5 volts, I needed more at terminal 1 for my U1. Like if I want 5 at the output, 1 should be more than 5. But the battery that I was using, it was rated at 4.8 volts. And the capacity it was having, it was 2,300 milliampere hours. So I changed that battery to a 9 volt battery with a less capacity so that it can charge more, but I was not able to do that test. So the battery voltage is 9 volt and the capacity is 175 milliampere hours.
Okay, so your battery is actually a 9 volt battery now.
Yes,
The 4.8
because to get the output for 5 volts.
Right.
But
you
if
should
I
say that your input's
use
lower than-
4.8 volt, I was able to turn on the LED without the U1, but after a few times the intensity was reducing as the battery was discharging. So I wanted to keep the output voltage as fixed. So I added the voltage regulator, but then at the input I was getting less voltage.
Well, you're tossing out 4 volts or 3 volts or whatever. The LED 3 requires how much across its terminals?
The voltage,
Yes,
it's 5 volt.
it's a 5 volt. So you're tossing out 4 volts as heat, 4 volts with however much current as heat from that 7805 then. So you're probably not gaining much.
Does LED 3 require a resistor?
LED 3 required resistor?
Yeah.
No, sir.
Why not?
Because when I was trying to do that, it was giving me a voltage drop that was reducing the current and the intensity was getting impacted.
From the data sheet, does it not require a current limiting resistor?
No.
I think what you required was a constant current regulator. Is what it should be. It shouldn't be a 7805, it should be a constant current regulator. Determine what current goes you need to go through your battery, your LED, and get the regulator to deal with that. Because that could potentially hurt your LED in there.
Also, I did the calculations for R3 based on the LED voltage, forward voltage drop, considering the green color and the red color, and it came around 222 ohms. So I selected the R3 as 220 ohms.
Well, that's another question I had. Red and green LEDs are inherently different,
Forward voltage drop, yeah.
well, not just that, they have different forward voltage drop and they have different perceived visible intensities. You need to look at biometric as opposed to as radiometric and or physiometric, sorry. And so therefore I would assume that your two LEDs are probably, one is brighter than the other one. And that's because you're sharing that one resistor, which, again, depending on how important it is, that the LEDs be the same.
The red LED is having a forward voltage drop of 1.8 to 2.1, while the green is till 2 voltage drop. So I have considered both and I've selected a middle value as forward voltage as 2.
Doesn't change what's happening at your
Yeah.
LEDs.
So I did calculate it for the maximum and it was nearly coming around 202, so I selected 220 as my.
That still doesn't change what's happening at LED 3. Can you bring up just one last thing? You had the discharge time of your battery. You had a slide there.
From digital.
So you can clearly see they show you how they calculate the time. You really didn't need this. All you need to do is know that battery life is battery capacity divided by load. That's not a super secret formula. My question though is, it says it's going to last 8.667 hours. Is that really how long it's going to last?
So it depends upon the ideal conditions. This is tested. Assuming that device consumption is 300 milliamperes, so it doesn't stay at good temperature.
Let's assume your battery draws 300 milliamps on that 2600 milliamp. Your battery's going to last for 8.667 hours. Your device is going to operate for 8.667 hours.
It will be more depending upon.
It will be a lot less.
If
You just mentioned that at 7805 you were having problems without it, with the battery, the LEDs falling below 4 volts.
So
This assumes that you can draw it on your battery till 0 volts, and your device will work till 0 volts. That's untrue. That's untrue. Your battery, first of all, will have a knee. It's not linear, okay? And second of all, your device cannot work under, I don't know what voltage. Let's say 7 volts. So this linear reality is it needs to stop at, I'm guessing numbers here, at 7 volts. So all that remainder of time doesn't apply. Okay? It doesn't apply at all. And in fact, I don't think you can bring those batteries to 0 anyways. You'd probably ruin the batteries if you did. Right?
no, we don't discharge it completely. Yeah.
Well, that's what this says. This says it could discharge the whole thing completely. There's nothing here saying time-wise. It says it's a 2600 milliamp hour battery, and you're drawing 300 milliamps from it. How long will the time be? It's going to be 8.6. That's the math there.
I roughly calculate time for my battery, keeping 60 milliamperes capacity.
But it doesn't matter. It doesn't matter if you change the numbers. The formula is incorrect for what you're trying to attempt to say.
Consider the data sheet and see.
Yeah. The battery's discharge is not from here all the way down to 0. It's a knee that falls down, and when you fall below a certain amount, your device won't operate. So it'll stop operating, it'll start drawing current, whatever. So that will be the length of your operation time, and the rest of it is null and void. So it'll fall quite short of that. Try it. Try it, let it go, and it'll fall quite short of that. If the numbers you have, whatever numbers you have, You plug it into that formula, you don't need this calculator, plug it into that formula, it's gonna give you this value.
It was
And
giving me 48.
And I'm sure you're gonna fall quite short of that. Because again, you have a minimum voltage operation for your device. So this assumes your device can operate till 0 volts. Impossible. Impossible. Even if you say, well, yeah, you know, the LED, well, no, the LED needs it needs 5 volts, right? And even if it didn't, if it was an incandescent bulb, you still, that bulb after a while, you have a minimum luminescence that you want to operate at. So if you had 1 volt, 2 volts, it's not going to be strong enough anyway. So there's always a minimum we can operate at, right? Okay. So those are things you have to consider here.
As I said, I still have the test to complete with the weather conditions. If it is sunny, I still want to do the test for my charger.
Yeah, well, that's fine. That's a whole other,
Yeah.
but this is not what you were testing here. Okay. All right. Thank you.
Thank you.
See you tomorrow.